Okay, hello everyone. Welcome to PROPL 2026. PROPL stands for Programming for the Planet. I'm Cyrus, and I'm listing the co-organizers of PROPL. Anil couldn't be here today, but he's planning to join this afternoon remotely and serve as sort of our scribe. I'll talk a little bit about the logistics of our living document in a little bit. Dominic's here and helps a lot with the organization. Thanks, Dominic. And Casey, I believe, is not here either, right? Yeah, so, but also helped organize the workshop. So thank you all for coming. This is a little bit different from a normal workshop at a conference like PLDI. We're very motivated by a particular problem that's sort of outside the traditional computer science set of problems. It's the problem of planetary health. And in fact, this is a crisis problem, right? This is a problem that's sort of acute and getting worse every year. If you look at this warming stripes visualization, I think this is a really nice way to sort of see the progression of the temperature, the Earth's temperature over time. This one ends in 2022. You can see it's already getting very, very red. If you look at the last 3 years, these are actually hotter than all of these. So the last 3 years were the 3 hottest years on record. And previous versions of this slide, maybe last year even, would have said 420 parts per million. It's now exceeded 430 parts per million at the Mauna Loa Observatory for the first time this year in 2026. Okay, so this is pretty bad, and probably don't need to convince anyone in the room, but this is largely due to kind of the industrial actions of humans. So if you kind of model just the natural solar and volcanic changes that would occur in green there, those are kind of flat relative to what's observed. So this alone is a crisis, but let me kind of put some underline this point a little bit more. This has an impact on all creatures on the planet. So there's a massive biodiversity loss that's occurring right now. If you look at the WWF's Living Planet Index there on the right, you can see this catastrophic decrease in monitored wildlife population. So the Living Planet Index is basically if you take a baseline in the 70s of species populations in various places, average them out, and you keep looking at that data, it's down 73%. Okay, so catastrophic loss of biodiversity. There's also a catastrophic danger to about 1 million species that are threatened with extinction, and a number of others that are threatened with massive loss of habitat and other things like that. This has an impact on one particular animal that we care a lot about, the human. I just picked a few impactful things that are going on. If you look at water services, this is actually something that's improved in recent years, but is still in crisis, sort of access to safe and well-managed drinking services. It varies, as you can see, a lot by country. But the impact of this is that 1 in 4 people, 2.1 billion people on the Earth today, lack safely managed drinking water. And climate change is going to intensify things like droughts and floods that could potentially make that worse. Okay, so if you work in these areas, if you're the kind of person that produces graphs like this, you have to you sit with these kind of catastrophic numbers, and you come to work every day because you're motivated by doing the work to make this better. And so I think all of us at some point have had this thought of like, what can we do about this? And I want to frame this as kind of a question of a collaboration or coordination. It's a massive group of people on Earth that care about these issues. It's not everyone, unfortunately. And in fact, there are people that are kind of like opposed to doing anything about these issues. And that can be a bit deflating. At least for me, it's very deflating sometimes. But if you just take all of the people that do care about these issues, it's billions of people, a massive group of people that could collaborate and do something about this. We don't need to convince everyone, but we do need to convince ourselves of what we need to do. We need to figure out what we need to do. I'm not going to say anything that is particularly surprising here, but there is a lot that we can do. I'm going to start kind of big picture and then zoom into what we can do as computer scientists and computationally literate scientists in this space. So, big picture, we need to work to understand the dynamics of all of these interconnected planetary systems. So roughly gather a lot of data and use it to develop and refine models so we really know what's going on, so we can understand, for example, the scale of biodiversity loss both globally and in individual places. And then using these models and using these data and doing hypothetical reasoning, we want to, so the first bullet point is basically do science, okay? The second bullet point is do policy, right? So propose and analyze potential interventions that might help with this crisis in various ways. This requires doing this sort of hypothetical reasoning about potential interventions, informed by the first set of works. And then finally, we need to create kind of these conscientious social movements and organizations, or modify our current organizations that do all the human work that needs to happen here. So that coordinate all the different stakeholders that are all over the world, that are in all sorts of different areas, including the press, including the broader public, to create the necessary support to actually initiate these proposed interventions. The proposal actually needs to be effectuated at some point. And then it's not just enough to initiate, you have to manage and execute these interventions effectively. And then there's a lot of room for supporting roles here. So to support all of these activities, and think of yourself as part of this ongoing planet-scale collaboration, right? And I think that's actually where a lot of us are going to end up sitting, right? We're not maybe scientists working on modeling water, but we want to support people that do. I'll come back to that. So this is a race that we are losing, but it is a race that we can win. That's what the Secretary General of the UN, Guterres, said. And I think with the help of computer science is what the attendees of PROPL can do. All right. This book, 5 Times Faster, sort of also underlines this, that as you can see with the tagline up there, pace is truly what matters in the climate fight, that it's really, this isn't something we can punt to the next generation, or really even punt to the next decade. We need to be working now to address these crises. An extinct species doesn't come back. So some quotes from this book. Still, our appreciation of the risks of climate change is limited by the way our academic institutions encourage each researcher to focus on their own narrow area of expertise. You can think of this as a critique, but it's also, it's just an observation about many of our realities. And then any actor should understand their points of leverage. We each have to understand the opportunities presented by our place in the system and do our best to exploit them. Okay, so we might, this sort of narrowness of expertise can also be a place for us to think about, stop being overwhelmed by the big problem and think about our individual place within this big collaboration that we're doing. Okay, so coming back to this list of things that we can do, I want to reflect on some of the past workshops a little bit, which have really touched on aspects of all of this. So PROPL is a fairly recent workshop. It started in 2024 at POPL. The fun naming, I guess, is a little less fun as we move to different conferences, but it's still fun. So PROPL 2024, I think, was very interesting. It brought together a lot of practitioners that told us about the way they are doing modeling and analysis, the way they're building tools for one another. We talked about various particular areas like energy and efficiency. And then we had a lot of discussion about software engineering practice and software engineering ecosystems and tools, and both the state of the practice and potential future directions. And there was discussion about things like policy and decision making in our roles in those kinds of processes as well. So I encourage you to go back to PROPL 2024. I believe there are YouTube videos of many of the talks, and there's material online. This is no less relevant, all these things are no less relevant today than they were 2 years ago, arguably more relevant than they were 2 years ago. And then we've been shifting PROPL around to other SIGPlan venues. So we had PROPL 2025 at Splash, ICFP Splash last year in Singapore. That was a very big event because of the co-location, so there was a lot of engagement there as well. There was a little bit more kind of focusing on the programming part of programming for the planets, but lots of interactions with practitioners and domains of practice there as well. Programming for biodiversity was a big focus. What are the principled ways to do scientific programming, which was a big bridge into our community. And then lots and lots, I mean, throughout all of this, there's been so many great talks and exciting demos and concrete applications that we've been able to enjoy. There was a poster session. We also did a proceedings last year. So there are some published papers out there that you can read in addition to the talks and other material. This year we're going to go in a little bit of a more narrowed and focused direction. After discussion with the other folks organizing, we thought it would be good to focus on this kind of last bullet point because it kind of encompasses the others. How do we, as researchers in a community like the PLDI community more broadly, or the SIGPlan community or the systems and software community, support all of the above activities with this viewpoint of thinking of this as an ongoing planet scale collaboration. And so today we're going to have kind of two sessions. We have this morning session, and then we have a more open-ended afternoon session. In the morning session, we're going to have 4 position papers that talk about the sort of the computational fabric, the infrastructure of the planetary compute engine that might drive future work, the sort of coordinating activity of all these different kinds of computation that's happening. I'll talk a little bit more about that. And so I'll let all these speakers speak for themselves in the next couple of hours. And then the second session is going to be a kind of a guided design discussion. And I'll talk about that in a second. I want to motivate a little bit of like what we're doing this time, because it's kind of grounded in some of the stuff that we talked about over the last 2 PROPLs. So I'm going to take advantage of the fact that I'm up here to show you some of my slides from last time, slightly modified. So these workflows that all of these people engaging in all of those activities are doing, they're these sort of loosely coordinated large-scale collaborations. This isn't the sort of thing where we're all having a group meeting and coming to a decision and there's one leader, right? These are distributed collaborations. And so we need to identify kind of best practices and permeate these through the community in order to make these collaborations effective. You're sort of collaborating with people you don't know, collaborating with future people, collaborating with people that are in completely different kind of communities than what you're used to. And so there's been a lot of thought in the community around large-scale collaboration, large-scale science. Open science was the big catchphrase for many years. And so some of the criteria that have come out of those discussions have been published in various papers. I like these criteria, the FAIR criteria, but there are lots of papers in this space. But let me kind of center our discussion on the FAIR criteria. I think this gives us a nice vocabulary for talking about design discussion. So the FAIR criteria it stands for findability, accessibility, interoperability, and reusability. I'm also throwing another R in there in the spirit of reading, writing, and arithmetic, reproducibility. Okay, so what are these briefly? Findability. So these are criteria about kind of like the artifacts that we produce in the course of scientific workflows. I use the phrase data in code here, but I guess you can include other scientific artifacts in this as well. So findability, data in code should be discoverable by people and machines. This isn't always the case. In fact, in many cases, when you're doing scientific work, your data and code is on your workstation, not findable by anyone, right? So these things don't happen for free, and I'll talk about that. Accessibility, kind of related to findability, but it's once you've found something, you have to actually be able to access it, and this requires thinking about who's accessing it, what abilities that they have, and kind of what form it has. Is it accessible? Is it a 10 terabyte data set? Is it a 100 terabyte data set? Oh, maybe that's not going to fit on a laptop. Then you have to provide some way to access it in a more incremental way, right? So those are the kinds of concerns that come up, especially as kind of science scales to this planetary scale that we care about in this field. Interoperability, a very familiar word in a community like PLDI. Code should interoperate with different data sources, with different tools, with other code. And as we know, there's not a single programming language or standard in many of these cases, and so you need this sort of open-ended interoperability and kind of a focus on this in order to make it possible to build these large-scale collaborations with people that have many different skills and tools. And then the R, reusability and reproducibility, it should be possible once something is produced to run it, modify it, build upon it, and the reproducibility angle is not just once in the moment that it happened, but repeatedly. So you can't be sort of contingent on the current state of a database about the world in order to reproduce a result, so you need maybe things like versioning and controlling dependencies and various other things. So we'll get into all of these specifics as we talk today. And then I threw in this additional one. Some of you might know that I work in live programming as my main gig. But I think this is actually quite relevant in science because liveness is all about sort of things changing as you work with them. And in a field like planetary science, of course, the planet is changing continuously because it's a dynamical system. And our information about the planet is kind of like changing continuously. I was about to say increasing monotonically, but sometimes things like disappear off the internet if a certain government has its way, right? So we have to think about those kinds of things. So liveness, right? We can't just have something be kind of a frozen snapshot forever, although that's important for reproducibility. We also need to be able to update our view of the world as it changes, and it's changing very rapidly due to human action. And so I hinted at this, but I think a core problem we should be thinking about here is bad defaults. This sort of patchwork of software tools we use to do scientific work today is, like, broadly construed, requires putting in a lot of extra work to follow these best practices. This is something that you do, like, you write your paper, you do it in kind of the hacky way, and then you, like, if you really are conscientious about these things, you might go and spend another day trying to ensure these other things are there. And I think some of that might be necessary, but I think if the tools had better defaults, where like through the course of your normal work, without having to think about it, some of these things happened by default, I think that could solve a lot of problems. And that's an observation from design more generally. That's not just an observation in this field. It's, people kind of follow the defaults, and it takes a lot of mental energy to like deviate from a default. So if we design defaults really well, I think that can be really important. That was my point there. So, for example, consider computational notebooks. A lot of scientific work goes into computational notebooks like Jupyter, and these are very powerful and effective tools. They support, interleaving code and things like visualizations and prose. So there's a lot to like about computational notebooks. But if you evaluate their design according to these criteria, you get you sort of see that they're suboptimal, that we could maybe do a lot better. So let me just kind of outline this. Findability, right? A computational notebook, your notebook is living on your notebook server, which is often your workstation or your lab's workstation, or something like that. And so it's not really discoverable by anyone else by default. And it takes a lot of effort to kind of make it public and kind of turn it into something that other people could find. And so if you're taking a data set and cleaning it up and analyzing it in a certain way, someone else might end up doing the same thing because they just don't know that you did that. They don't have access to your code, or there's too much and they can't find the exact thing that they need for the thing that they're doing. So findability, I think, is very poor in the current state of practice. Accessibility, I think it's kind of related to findability in this sense, but in this setting, but data and code should be retrievable in an accessible form. There's lots of stuff that isn't retrievable in a computational notebook, like the order of execution of cells, for example. There's also a lot of traditional accessibility issues with notebooks, like a visualization is not really something that someone with visual impairment can see. And there's actually people working on that, visualizations for people with visual impairment. Very interesting area, I think. So lots of questions around accessibility. The form of a notebook is also this sort of JSON blob that has not a lot of computational structure in it. Interoperability, this is really bad in a computational notebook, right? You have a notebook with a bunch of code in it. Other notebooks have no access to one another. You can do, there's like a library import you can do in Python where you execute another notebook in your current notebook, But if all you needed is one routine in that notebook, you've suddenly loaded this entire other data set into your state and then thrown it away because you're just calling one function with different data, right? And so interoperability, even if you just think about working within Jupyter notebooks, within Python, right, it's still bad. And then you think about the bigger interoperability problem of people are using different languages, not everyone's using notebooks, et cetera, right? So that could be improved a lot. And then reusability and reproducibility, I think, also connected to interoperability here, but it's not easy to rerun, right? You have no log of what was actually run to produce the notebook state because it's a out of order thing, and there's a heap that is separate from the actual state of the editable artifact. Modifying and building upon these things source largely through copy and paste. In fact, there's some data out there that says it's like 70% of scientific code is copied and pasted from other code. 70%, right? Okay. And then liveness, right? These things are not live, right? If the upstream data changes, the notebook is not going to re-execute or show you anything new. You have to explicitly go and do that. Sometimes that's what you want. Other times it'd be nice if there was a nicer interface to data that's updating constantly. If you have a satellite taking photos every day, maybe it'd be nice if your current, you had some way in a notebook to get the current state and also snapshot states of the past. And so last year, the talk that I gave proposed this system. This is a completely hypothetical system at the moment. And so I'm not sort of like plugging a thing that there's not like a GitHub Fairground repo or anything like this. This is just, it's nice to give a thing that we're building a name. And the design of this is really up to all of us. But roughly what we envision is something more collaborative and fair and live. That's still kind of based on some of these ideas. We're not going to completely change the way everyone works, but we want maybe a computational notebook system that operates more like a digital commons. And not just a regular digital commons, but a computational commons, one where thousands of these scientific artifacts, data sets, notebooks, plots, sensor configurations, et cetera, are authored and collected and maintained, not on our individual workstations or in our labs, but collaboratively in this kind of bigger collaboration that we're a part of in an executable and interoperable form, more generally in a manner that is fair and live by default, that kind of engages with this design principle of good defaults. So this is inspired by other digital commons that have been very successful, right? Think about Wikipedia. This is a big digital commons that a lot of people have contributed to, that has improved humanity in a lot of ways. You can also think of GitHub as a big digital commons, or NPM, or these big Linux package managers. These are all digital commons. These are things that people collaboratively contribute to for the benefit of everyone contributing to and using these commons. The thing I want to point out here is that these are largely file systems. These are all file systems, right? Wikipedia is a big file system for whatever the wiki markup language is. GitHub's a big file, literally a big version file system, right? NPM, all these things. What's not kind of inherent in the design of these things is computation. It leaves computation to the client of the commons. You get an artifact from these things and you run it locally. The thing that I think is worth thinking about is integrating computation more fundamentally into our digital commons. So the way I like to think about it, this may or may not resonate with you, but it resonates with me. If you think of something like Wikipedia or GitHub, instead of it being a big database or file system, as a massive live program that's executing and being collaboratively edited at the same time by thousands of contributors. These could be humans. These can also now, of course, we have swarms of AIs that are doing things, right? And we can discuss the design of that particular group of editors. But what if we had a big, massive live program? Well, if it's a big, massive live program, there's a lot that we can do. We can do things like findability could be find all uses of this data set, right? Find all uses is kind of a semantic operation. It's not a text search. You could do things like refactoring across the giant monorepo of all of climate science. In fact, if you haven't heard the phrase monorepo, right? If you go and work at big tech companies like Google or Jane Street or other things, they put all of their code into one big giant version control system. That's a that's a digital commons within their organization. Why do they do that? So they can do things like find all uses and do refactorings and keep everything up to date with the current state of the data that they have that they're working with, et cetera, right? And so I think we can actually learn something from these big organizations. They have some different design constraints, right? They have kind of more centralized leadership and things like that. But I think some of these things are maybe relevant even to these more distributed collaborations that we do in science. Okay, so anyway, some more stuff that we did. So Alexander, who's here at PROPL 2024, we started thinking about this problem back then, and we started thinking about it from the user-centered perspective. So we proposed a sort of user experience. We think it's important to have computational notebooks, but also have kind of other authored artifacts, things that like journalists and policymakers and so on can also interface with. So more of a kind of authoring document editing environment where you can drop into the code backing different things. This was our prototype where you have kind of a table and a map, but these things are all code underneath, and you can kind of like dig in and see the code and then work with sliders to change parameters in the code and so on. So since PROPL 2024, we've like built a bunch of this stuff. Ask Alex or me for a demo during the week. At PROPL 2025, a lot of the discussion in my talk started to discuss things around languages and systems, right? If it's a single massive live program, well, what language is that program written in? And of course, the answer that we came to at PROPL 25 was Fortran. No, okay. I mean, that could be an answer, but really the answer isn't any one language, right? The scientific code is written in many different languages by many different communities, and we can't actually force everyone to switch to one language. And instead, let's do that XKCD thing of like, well, let's come up with another language that serves as an orchestration language and design it so that it really makes working across all of these different things more suitable, more practical. And so that turns into a language design question, which is very relevant to PLDI. And so if we're going to design this orchestration language, what are the design criteria? Well, I think if we're going to motivate it by these criteria, we can kind of use this as the starting point. So if we're going to support findability, we have a giant, massive live program. You can't just do Command F and VS Code, right? You need things like indices and querying over this. To support accessibility, you need things like thinking about access control, the computational resources. Where does the compute actually happen? Is it co-located with the user that's actually working with a particular artifact? Is it co-located with data that it's accessing? Data format design and kind of protocols around standardizing data formats. Lots of UI design questions around accessibility. To support interoperability, that's really an orchestration language needs fundamentally support interoperability. So there's lots of interesting research questions around what a good foreign function interface could look like. I think that's a topic that many languages have FFIs, but there hasn't been enough research on FFIs, I think. I think there's lots of designs that haven't been explored yet. You're not just interfacing with foreign functions, you're also interfacing with foreign data, databases that live elsewhere, and how do you interface with that in a way that integrates with the semantics? And then many of us in this community, I think, are big fans of type systems as ways of mediating the interfaces between components in a system. What is the type system of this orchestration language, and how does that interact with the type systems or lack thereof of other languages that are being used? To support reproducibility and liveness, we need to do things like control dependencies and side effects. If you just have uncontrolled side effects, reproducibility is almost impossible. Liveness is almost impossible. You don't want, on every edit for it to kind of hit your database and download 10 gigabytes, and then you change one character and it does it again, right? So like you have to control side effects. And then to do this all at scale, you need kind of the bread and butter of a lot of PL research. There's a lot of open problems there. Incrementality. If you make a small change, you don't want to rerun everything in the commons. Parallelism, right? You can't sequentialize everything in the commons. There's not a sequential order of all scientific artifacts. It has to be inherently parallel. It has to be distributed. There's not all running on one machine. There can't be any gaps in execution, right? If I like make a mistake somewhere when I'm editing something in the commons and I commit it, or I go and get a cup of coffee, I can't have that bring down everything the way a traditional type checker in a programming language would, right? And so lots of interesting questions related to liveness at scale. So this is very big thinking, right? Like, what if we designed a massive live program and solved all these problems? I think this is the right time to do this kind of big thinking. This would be kind of pie in the sky stuff maybe a decade ago, because, well, then somebody would have to like take all the resources, all the things everyone has built over the last many decades and kind of incorporate them into this new system. But now we have this opportunity, I think, some of you might disagree, for kind of ingesting things more quickly, right? As we solve these PL and systems and HCI problems, as we build the system that should exist, the adoption cost structure has changed a lot, because the kind of costly and boring work of integrating prior stuff that people have built into this system, you know, like taking a library and building bindings for it in a new FFI. Who wants to sit around and do that? Well, you know, maybe an AI really loves doing that, or at least can be convinced to. Maybe not, right? This is an empirical question. There's also a question of sort of like what values do we have as a community about AI, but I think it's worth considering this at least. And then, of course, there's lots of socio-technical questions beyond this, right? This is meant to be something lots of people contribute to. What incentive structures exist for contributing, right? We should maybe design those in the same way we design the system itself. There's going to be some level of training. How do we build scalable training? How do we actually get this in the hands of people? Or maybe not scalable training. How do we give something to a PI that they can give to their students and feel ownership over? Shared governance, right? This is a big system. It's going to be governed by, you know, similarly to like Wikipedia. There's going to be governance and rules and like sort of what are the procedures for that. This is going to cost money to build and to sustain development. What are the funding sources for this kind of thing? And this is not going to all like come out of our heads today in one Google Doc later this afternoon, right? This is going to require participatory design iteration. Participatory meaning with the people that are going to use this. Some of them are here today. Almost all of them are not, right? So we need to get ourselves out into their world, look at their problems, and try to solve them using tools that we think maybe are better, and we'll probably learn that they're not better, and then we'll iterate. And at some point, maybe they'll become better, or we'll learn something really important and write papers about scientific programming practice and how they're actually doing it in a way that like surfaces problems that we haven't considered. And then the benefit of all of this stuff should be kind of broadly distributed. It should be equitable, right? We're not from those countries. Most of us are not from those countries where the map earlier showed a lot of water scarcity, for example. But we're trying to help. We should engage with those people. We should make sure that we're not sort of the benefits of this system are not just going to the places that don't need them the most. Okay, so I'll stop there. This is what, this is one framing. I think it's useful to have a concrete framing rather than to have an open-ended discussion about all of programming in the planet. I think it's ripe to do a kind of design discussion like this. But if you think I'm missing something, or that we need to think about something that's just not been brought up at all, this afternoon is your opportunity to do that. So it's going to be a series of guided discussions. Roughly, it's going to look like a 30-minute session-ish for each of these topics. User experience, I think grounding everything in like what will this feel like as a scientist to work in is really important, so that's where we start. And then things about like the programming model and interoperability and scaling and AI stuff, socio-technical stuff. I'll give a very brief reminder of kind of some of the big problems before we start each of these sessions, just a minute or two, and then we will discuss. The way we're going to do the discussion is we have this living document. I'll leave this up for a little bit if you want to scan the QR code or type in the link. It's just a Google Doc. Once I see everyone's cameras down, I'll open it up. So this is really meant to be just a space for you and also Anil later will be our scribe to to take notes, to ask questions that you want brought up, to make comments, to point people to things that you think might be relevant that maybe not everyone knows, right? If there's a great paper about this that, that is worth checking out, leave a link to it. I want to encourage everyone to contribute to this, not just the senior folks. If you're new to this community and you have what feel like naive thoughts, naive questions, great, right? That's really important knowledge for everyone. Like, what are the things that are confusing and what's on your mind, right? I think that fresh perspective is often quite valuable. So please contribute to this. I'm going to use the document as the place to kind of like decide who maybe is going to start talking out loud. So sign your note or whatever if you want to be kind of called on. Yeah, and if you see anything, if there's anything logistically here that you think could be better or whatever, go for it. Also, if you want to like +1 things that you think are interesting, that would be great. It's just a Google Doc, so use it however you want. Okay, and then one last note here. We will have an informal workshop dinner this evening. We have a reservation at SALT at 7 p.m. That's at 1047 Pearl Street. If you want to coordinate on walking there together, 7 p.m. is a little bit after the end of today's events. So if you end up going back to your hotel, then you can just meet us there. But if you're still around here and you want to coordinate, maybe leave a note in the living document. There's a section at the end. Okay, that's not a formal workshop dinner. That's just we reserved a couple of tables there, kind of situation. Okay, so I think that's it. Let me actually just pull up this document and show you kind of what's in it. Where are we at on time? Okay, that's about right. Great. Okay, so this is the document. I'll try to get, in the break, I'll try to print out this QR code on a sheet of paper if you missed it. And if you want to leave any notes or comments on the introduction, you can do that here. And we have sections for each of the talks that are coming up. One thing I want to note is feel free to leave notes ahead of time. You don't need to wait for that session to start. If you're I want to bring up this in the AI discussion, or I want to bring up this in the interoperability discussion, and you want to take some time in a break and get your thoughts together and write something down, perfect, right? Let's do that. Other than that, consider signing your comments. We'll have a discussion towards the end here about what we actually want to do in terms of after this workshop with this document and as a community. Is this just for us, or should we create something more public? But that's it. Okay, thank you. Excited for a fun day. Okay.
Thank you. All right. So thanks to the organizers for inviting me here. I'm pretty excited. As was said, I am not a computer scientist, so I would never have shown up at PLDI. But I'm actually quite fascinated. My name is Flatirons. So yeah, I have a PhD in physical oceanography. I was a researcher for quite a while, and then I got pretty deep into the open source scientific Python ecosystem. And then today I work at EarthMover, which is a startup filled with people like me who decided that software was holding back research, particularly and human response to climate change. And so I'm going to tell you about where we came at this problem, and specifically talk about a project we've been cranking on for the last 2 years called IceChunk. And I'm going to put that forward as this is the storage layer you should consider for anything you're building. It takes a lot of ideas from Earth system data systems over the last 30 years and tries to smash them up with all kinds of new things that I think are fairly standard in the computer science world. So the point, speaking as an Earth scientist, we needed a new storage layer, and we built IceChunk to be that layer. So it's kind of a newish, it's only about 2.5 years old, an n-dimensional array storage engine. It is designed to be cloud native. I'll kind of clarify what that means. It is open source, Apache 2.0. It's a Rust code base. We welcome contributors. It smashes together a number of what we think are very good ideas, both from the history of Earth system data systems, as well as databases. I view it as kind of increasing engineering rigor in the Earth data ecosystem. I've kind of started diving into lightweight formal methods, and now this idea of rigor has really resonated with me. We think it's a great foundation for computational systems, like the one you guys are going to be discussing today. And then EarthMover, which is the startup I work at, is building a kind of cloud platform for planetary scale data federation. I'll talk to you about how far we are along there and where we see things going. So yes, we have an extremely broad mission statement, which is to empower people to use scientific data to solve humanity's greatest challenges. It's all well and good. Really, it comes from we were all scientists who felt that software held us back, and we need to do something about it. We need to do it fast. And so we're a venture capital-backed public benefit corporation. Our founders are Ryan Abernathy, who was previously a professor at Columbia. We overlapped with grad school at MIT. Joe Heyman, who was also a startup, Carbon Plan, and then we kind of overlapped at NCAR as researchers. We have a bunch of customers, but the thing I would emphasize with this group is we're starting to see uptake in public sector agencies, and that's really important in the Earth science because those are the people that collect massive data sets. So we're talking about NASA, NOAA, which is the National Oceanic and Atmospheric Administration. They're the guys that do weather forecasts, launch satellites, a bunch of other stuff. The UK Met Office, ARIA, which is the UK's version of ARPA. So yeah, my name is Flatirons. I would call myself a professional scientist for about 13 years. I started grad school, eventually landed up NCAR, which is up the hill here in Boulder. I did kind of terabyte scale ocean modeling, both small regions of the ocean, as well as thinking about the whole global ocean. That picture up there, bottom left, is a very pretty picture of the tropical Pacific sea surface temperature. It shows you the cold tongue. That's a very La Nina system, so we are now in an El Nino. It does not look like that. It is much warmer. But the ocean is very pretty, and this is why I love my job, right? But my job also involved wrangling terabytes and terabytes of data distributed in many files, and it was painful. It was extremely painful. And so Ryan and Joe started this project known as the Pangeo project, which was in about like the 2015 range, where we were seeing cloud systems coming up. The kind of older data systems were kind of showing their age. The code was all single-threaded. Things were too slow, couldn't keep up with the amount of data we could generate. I like to joke, like, if someone asked me what size of data do you work with, it's like, what size do you want? I could generate it. It's so easy, right? You just output more. And so we kind of all coalesced around this project known as X-Array. I don't know if any of you have heard that. It's a few people. So X-Array is an n-dimensional analytics package. Its core idea to me is that you can use metadata to help you express data analytics. So the easiest example, you have temperature. I can say, take the mean along the dimension time. And this is a massive improvement over what we were doing before. Say in NumPy or MATLAB, you say temperature.mean axis equals 0. What's axis 0? I don't know, right? So I have to keep all this context in my head. X-Array lets you put the context in the code. So It's readable, it's reproducible, it's so much better. So we were all kind of doing this open source thing, grant-funded projects, and it all just felt a bit too slow. And we felt that the Earth science, scientific data, and compute landscape kind of needed a big upgrade. Why is that? Here's 2 examples. The first I'll talk about is weather forecasts. This is from ECMWF, the European Center for Medium-Range Weather Forecasting. They are basically the world's best professionals at doing weather forecasts. They've been very good for about 10 years, at least. Here's the way they distribute data. They have a format called GRIB, which is gridded binary. It dates back to the 80s. And it really is a transmission format. It's a file that's really concatenated messages, and it's encoded binary data. A private sector customer, for example, will pay them to get fast delivery of these forecasts. The way those get delivered is a GRIB file gets dumped into a cloud bucket. A notification flows out to someone's script that triggers off a Lambda, does a bunch of stuff on it, right? That gets repeated for every customer. So they're just shipping out, like, I don't know how many copies of the same data to multiple people in different buckets. It's kind of crazy. And it's using a format that is extremely hard to work with. It's so hard to work with, we have, kind of explicit opinions on stickers, which I will not repeat. It incites a lot of strong feelings, the GRIB format. They have an archive, an extremely valuable archive for AI training. It takes a year to pull data off that tape system. You're sitting in a queue for a very long time to get data out of this, right? So like our data systems are quite old because the amount of data they're managing is very large. It's very hard to move. A similar example, a climate model archive. So this is the other end of things. So here, every like 5 or so years, there are big releases of what is known as climate model intercomparison projects, CMIP. So a bunch of climate modeling centers put out a bunch of data. Again, this is petabytes of data distributed in folders with about, 100,000 to 1 million gigabyte-sized files with a bunch of arrays in them. Handling this is extremely hard, and in effect, it privileges large institutions with large resources like NCAR. And so like having worked at places like this, and this is unfair. It's also crazy. I see why no one else can do it. It's just hard, right, to work with this kind of thing. Each of these archives is bespoke. That is the real pain point. And they shouldn't be, because they're all kind of very similar in like a conceptual level, right? And so it's mostly a reflection of the fact that these communities developed independently, and it was a lot harder to kind of collaborate back in the day, right? And so it was all kind of slightly different, and everyone does slightly different things. This pile of files model I've always felt it was very bad, and now I like this idea of it lacks rigor. You don't know what you have until you look at these files. Data may be missing or corrupt. It's hard to interrogate a pile of 100,000 files. You never know. Updates are invisible. If someone's putting new things in, it's hard to tell what happened or if it was even complete. And the worst is the users are not isolated from the physical data layout. So things like file names and how data is partitioned between files are suddenly a public interface. And this has bitten me so many times, it's crazy. So that's an example file name from a fairly important data set that NASA puts out for sea surface temperature. It's got a date time at the beginning. JPL is Jet Propulsion Lab, so those are the people that do it. Level 4 is a satellite data processing level. GRIST is the group for high resolution SST, sea surface temperature. This is the sea surface temperature field from the multi-scale resolution product, MER. It's a global field. I don't know what the first version string is, but the second one is version 4.1. But there's intense metadata encoded in file names. And I bet this audience knows about Hiram's law, right? The moment you expose any of this, it's suddenly public interface, and people depend on it, and you can't change it, right? And it's so bad. And it's even worse, right? So I've been talking about storage, but how do you analyze these things? Your first step is almost always you figure out how to scan these files, and you construct a cube. So you go from this kind of sharded representation in green to a nice compact cube, because that's how you think of data sets, right? Like if I think about air temperature, it's like, there's a latitude dimension, there's a longitude dimension, there's maybe a vertical dimension, and there's a time dimension. There's 4. I don't think about 100,000 files, right? And so there's always this mapping. There's this conceptual mismatch between storage and compute models that really just makes it hard, and it's incredibly duplicative work. a year ago, I kind of went down the rabbit hole of like, how did we get to this point? And it's like a fascinating story. I wrote a blog post. There's a talk if you want to read up on it. But basically, meteorological data infrastructure is extremely old. It dates back to the 1850s. It's one of the oldest examples of planetary scale infrastructure in the world. It's like older than the postal system. So it's completely wild and very inspiring, right? But I'm going to pick the story up in 1993, which is when a group of people got together to design the first distributed oceanographic data system. Considerable emphasis was placed on maintaining a research oceanographer's perspective as the focus during this development. So this was very cool because they were coming at it from like, we're building big systems for governments. What about us? We're the users, right? And so you should know that the two people, the first two photographs up there, those are professional oceanographers. Like the second one, Glenn Fleur, was on my thesis committee. And so they were getting together to try and figure out what a data system would look like if it works for them, right? And it's extremely cool. They came up with a few principles, which is to isolate the file format from the data user, right? A good thing. They wanted data users to be able to query data directly from packages and not, they didn't want people to interact with files. And they also wanted people to only extract data of interest from giant archives, right? Because a lot of the time, scientists say you're interested in a hurricane. You care about like 2 weeks of data, maybe. You don't need the full yearly archive, right? And so this report was very cool. It was very far thinking. And we ended up with the data systems of today, which is a composition of things like the CF conventions, NetCDF, OpenDAP, and threads. I won't assume that you know any of it. So like the high-level overview is you need a way to describe what's in your data. So that's the CF conventions, right? It has things like a controlled vocabulary. It says where an array is named with the standard name of this array is the sea surface temperature. It's controlled vocabulary. I see it as a user. I know what I have. It could be called anything you want, but you have this attribute. I know how to interpret you. Where do you store the data? It's a format known as the NetCDF. Think of that as an opinionated HDF5, if you've heard of that one. So that gives you a data model. It has groups, arrays, dimensions, coordinates. They came up with a technology known as OpenDAP, which is a way to access this data over the internet. And it does things like server-side subsetting of the data. So very cool. There's a lot of OpenDAP servers in the wild deployed by big places. They also had this thing called threads. This came out of Unidata, which is in Boulder, which is instead of presenting piles of files, you present cubes that people can interact with. So you interact with a thing that tells you, I have a lat dimension, a lon dimension, tell me what you want, right? And I give it to you. All of that was cool, but somehow it fell short. So I started as an oceanographer in 2010, and I used almost none of it, except for like CF and NetCDF. Like I had piles of files that were very nice, right? It turned out these things, they were used in kind of small sub-communities. And they were great ideas, but they were kind of implemented with kind of 90s, 2000s tech, and they couldn't keep up with computing systems of like the 2010s. And so in general, we found that, in my view, the more sophisticated ideas and services, like server-side compute and stuff, ended up being reserved for privileged data sets to like places like NASA and NOAA that could deploy infrastructure at kind of a bigger scale. And we kind of really fell short at the most research oceanographers are potential data providers as well as users, but most people don't want to run servers, right? It's just kind of just like a conceptual mismatch there that didn't really work out. And so we end up with kind of today's status quo, which is we have standards compliant, self-describing, very metadata rich. These are incredible properties, but they were still piles of files, right? And so we made a big step forward. I know people in other fields are very jealous about the earth sciences because we have great metadata and descriptions, but we still have a problem. How can we do better? The first thing, I'm not going to dwell on this too much. We think databases do it better, and they do it much rigorously. They have this idea of transactions, ideas of version control, ideas of formalized enforced schemas. These were things we wanted to bring to the earth science. A bigger thing, maybe more controversial thing in this room, maybe. We think the cloud lets us do things better, right? And I'm going to lean on this one idea of frictionless reproducibility. There's this paper known as Data Science of the Singularity. Have people here heard of it? Some nods? No? OK. Extremely good paper, very provocative. This is David Donahoe. He's a statistician. He's got one thesis, which is that we've seen an explosion in AI-related advances. And he's like, why? And he's a guy, he's been doing like data science for like 30 years or something, And so his thesis is that it wasn't one single algorithm. It wasn't any number of technical advances. It was like a social advance. He was like, what these guys have done is taken the idea of open data, re-executable workflows, and open challenge problems, and made them all frictionless. It is so easy to do that. That way, mode of working just took over the field. And because of that, they just kind of like kept building on each other, right? And specifically, he said, like, they've become frictionless open services. Example is GitHub, right? GitHub is massively inferential, right? And it's very easy. Once I see a repo on GitHub, I know how to interact with it, right? It's like these common primitives that end up being very powerful. He's got examples. They're not all commercial platforms, right? He's got examples of more open, federated platforms. But that was the kind of core idea, was that the cloud gives you this place where you can build these kinds of frictionless open services and hopefully kind of start triggering innovation. And it's a thing that we miss out on today because all of our data sets are just piles of files that are extremely hard to work with. It's like a high barrier of entry, and so people don't come in. There's been a recent explosion in AI weather models. A lot of it was catalyzed because Google took a very important product, ERA 5, which is a reanalysis atmosphere product from the European Center. They put it in a cloud-native format called ZAR and made it free for access on Google Cloud Storage, right? And so you suddenly had access to terabytes of data straight from Python, 5 lines in Python, and you could hook it up to your PyTorch model, and that just exploded, right? So like opening up these data sets, putting them in a nice place that's easy to access unlocks a lot. And so the core vision we've been trying to work towards is planetary scale data federation in the cloud. Our hope is that we can get university labs, startups, government agencies who are actually, they sit on piles of data, and even big tech companies, because more companies are putting up satellites, they're doing models, they're innovating on AI models, kind of how can we get all these people to talk to each other in a nice, fair way? And we think the cloud helps us do that. It's like a nice common place where all of these people can get together. So to do that, we needed a better storage format, an engine that could really understand that, and so that's where we've been working on IceChunk. It does a lot of things. I'm just going to go through it, and I'm around all day. Please, let's chat if you're interested. IceChunk is a chunked, compressed, n-dimensional array format. There's a lot in there. So what we do is we take a big array and you conceptualize it as groups of subarrays. So these little things are chunks. Those are subdivisions. And each of those is compressed individually, right? So that's a unit of compression. And then each of those gets stored as different objects of processing. So you can kind of parallelize across them. IceChunk is open source. It's Apache 2.0. The core is built in Rust. We did that because we wanted to really hammer performance. That's how you do cloud systems, right? They're high latency, but also you can crank the throughput, as we'll show you. It's got Python bindings, and we're hoping we'll get more soon. It supports arbitrary metadata, so we can take CF standard metadata and represent it. So we're kind of building on the good stuff that's happened already. It has this hierarchical data model, basically the netcdf, HDF stuff. So again, we're taking the good ideas, keeping them. It exposes data cubes. So we're trying to push that idea, don't think of files. The format controls how the thing is sharded on disk. The user should not need to know about it. And it supports n dimensions. This is very important. In Earth systems, you usually have 4 to 7 dimensions anyway. So lat, lon, vertical, time, an ensemble member for things, and then scenarios, right? IceChunk is extremely cool because what new did we bring, right? We're bringing this idea of rigor from database systems. So we have things like isolated sessions and transactions, things that have been known for be good ideas for a long time but haven't existed in our space. It is safe for concurrent readers and writers. Through isolated sessions, we have things like version control. So on the right is this is a fake data set, but it kind of illustrates to you the kind of Git style version branching and tagging and all this version control stuff that we can bring. We track changes through snapshots. So down here, each is an individual identifier for the state of the data set at that point in time. And so this is a good trigger for something like incremental downstream compute, for example. A little example. Usually the way you work with IceChunk, this is in Python, you kind of tell it a storage, which is where the data is. This is some public data sitting in US East 1. You open a repo, a reader creates a read-only session, a writer creates a writable session. A reader can open it into Xarray or some other package, kind of doesn't matter. The writer, on the other hand, could be constructing an update. They could be writing the update. It's all invisible until they call this commit step, which is at the point you seal a transaction, the branch pointer gets updated, and at that point, a new reader would see that update, right? The old reader is always seeing a very consistent state of the data. This is not true for any of the other systems we work with today. Parallel updates are very risky, but with IceChunk, they're not. IceChunk is very performant. The x-axis of this plot is, think of that as loosely time, and this is how we've been working over the last 10 years, basically. So it's 2015, 2016, this is kind of state of the art. We could push 1 gigabit per second through a 10 gigabit network card. Today with IceChunk, we can do about 7 to 8. So Rust helps us get close to saturating network hardware. It's very good, a massive step forward. My colleague likes to say, you make things 20% faster, that's nice. You make things 2 to 3x faster, 5x faster, suddenly new things are possible. And so I think we're kind of hitting that point now with our data systems. IceChunk is cloud native. Two perspectives on that. One, we keep metadata separate from data. And so it's very cheap to open an IceChunk repository and get a sense of what's in it. We'll tell you things like array names and dimensions and everything but the actual data is very fast and quick. We've made choices that are optimized for cloud object store. In particular, there's this cool little blog post. We got S3 to sustain 250,000 reads per second, which is a ridiculous number. But that's what you kind of need if you want. We're thinking of a lot of people streaming compute from an extremely popular data set, like a forecast, right? And so this is why we think the cloud is revolutionary. It's like you can do things at this kind of crazy scale that would be very hard to do with a classic server client architecture, right? This number is pretty ridiculous, though. A thing that I've been kind of pushing on over the last year is this idea of lightweight formal methods. And so we've been, we have big goals. We are a small team, and we need to move quickly. And so one of the tricks we do is be very careful about testing. So we have a battery of property and stateful tests, both in Python and Rust. We do things like concurrency permutation testing, pair that with some property testing because it would be too hard otherwise. We do fault injection tests because we have to talk to cloud systems, right, who are flaky networks. And so we have to be sure that we are good enough. And we are actually pretty careful about backwards compatibility now. We have cross-version testing that kind of smashes all of these together. Anyone here interested in talking more? I'm happy to do so. We've also got interesting blog posts and all the techniques we throw at this problem. This is starting to pay off. We are starting to see uptick amongst the public sector data providers. This is because they're all kind of moving to the cloud now, and a cloud-native format is extremely valuable. The National Weather Service just announced that they're going to be issuing forecasts in the IceChunk format. It's open, right? It's open source. And so there's no vendor lock-in here. And so that's a big part of it. ARIA, which is the UK's I think it's called Advanced Research Innovation Agency. So they have a climate tipping points research program. And so a lot of those simulations are hopefully going to be put on the cloud in IceChunk, so it'll be easy for people to access. NASA is extremely excited, mostly because we have this extremely cool feature. We can support virtual data sets that are basically symlinks to existing data. The way this kind of works is each of these chunks is a compressed binary blob object. And an IceChunk manifest maps a chunk key, so something like the chunk 0, 10, 30 across those dimensions to some kind of blob name, right, in object. That's kind of native. But a blob could just be a byte range within an existing object, like an etcdf file. And so we have an extremely cool project called Virtualize-R. This helps you construct these virtual queues from existing cloud archives, because the way a lot of these government agencies have moved to the cloud is that they've taken their folders and made them buckets. So we call it the lift and shift, right? But you've taken a format that was built for hype HPC networks, and you've put it on the cloud, and it doesn't work so well. And so we've basically by symlinking, we can get through that. And so here's a cool blog post about the GOES-16 archive. That's a geostationary satellite. There's like a petabyte of imagery sitting in the cloud. That is kind of hard to work with, but we can do better. Here's a little example. This is the NOAA GOES 19 in S3, one particular product. Here's how data is distributed, right? I click in for the year 2025. You get 3 numbers. Does anyone know what this is? Week. It's the day of the year. I've been doing this a long time. So if you scroll down, you'll find it will go to like 360 something, 354 for some reason. Click in. I think that's the hour. There's about 24 of them, right? You just click in. OK, I have 6 files. Who knows what's in it? Nobody. And it's got this very complicated format that even I don't know how to interpret. That is how data is distributed today, right? This is not friendly. It's hard. We're trying to do better. And so at Outmover, what we're trying to do is put IceChunk in the cloud and kind of really explore what a better thing looks like. Loosely, we keep telling ourselves we're trying to build GitHub for data, something that is that easy once you learn it, right? You do have to learn something, but once you learn it, it's powerful. One of the things we've been working with is a marketplace of data. Think of this as a clearinghouse for all kinds of things. We have free and paid data sets, academic, private, and public. And so I'm going to click over to what this looks like. So here, this is from an organization, a nonprofit called C-Trees. This is from a place, AI modeling company known as Brightband. They are just repackaging the European forecast in a pretty easy form. I'm going to go down here and search for GOES, which is that product I showed you. So this is one of those virtual data sets, right? I'm going to click in. Remember, I showed you the nested hierarchy of folders and files. So here's a little group. I'm going to click in. Turns out there's a little technical detail there. I'm going to click into another group. So this is a virtual reference of 367 terabytes. The whole archive is like a petabyte of imagery. Scroll down. This is what's in it. There's 6 dimensions. We got a few things in here. These are little sensor wave bands. If you wanted to, oops, I can't scroll. There you go. And these are all the attributes. They tell you what's in it, right? So this is the long name, ABI, cloud, and moisture imagery reflectance factor. Somewhere in here it will tell you what the band wavelength is too, and like how the thing is encoded. It gives you a link to the uncertainty estimate, tells you how the data was aggregated, et cetera, et cetera, et cetera. But this is 300 terabytes in this group. It was not copied. If you try to access this data, it will go to the original netcdf files that I showed you on the bucket and grab the right byte range that you've requested. So again, data cubes, not files. We're trying to like push the field towards thinking in terms of cubes because that's how the data usually is, right? And this thing is huge. That's a lot of time steps, 250,000 time steps over like 5 years. It's crazy. This thing is taking photos of the Earth every hour. Really every 30 minutes, I think, and then for this product, they process it to an hour. The other thing you get on the marketplace is subscriptions with notifications. And so this is pretty cool. I'm going to, oh, sorry, I should go back here. I'm going to click into this 15-day forecast. So remember, I was showing you this example of forecast data being pushed out as files. Here, we're trying to change that again. So it will tell you up there that this data set was updated 10 minutes ago. We've only requested 3 variables from the forecast provider. And I'm going to click into commits. And we'll tell you that 10 minutes ago, we did an operation. 4 hours ago, we started ingesting data 1 file at a time as they were landing in the bucket. So they're out of order updates. But because of IceChunk, writers and readers are isolated from each other. And so you can push these updates very safely without ever exposing a corrupt state to a reader, right? And so 4 hours ago is when the European Center started pushing forecast data out. And we were pulling it in and sticking it into our little system. And so you can go back and see the history of how this data was coming in. And you can see it's out of order. Like, these steps should be increasingly monotonic, but they're not. Like, that's just how the data comes out. Everyone kind of deals with this today. This is kind of our way of dealing with it. You can always figure out at any point in time, you can check out the state of the data as of that point, kind of go back. And so it's very auditable and all of these cool things. On any of those commits, we can start to trigger downstream workflows, incremental compute, all of that. That was a lot. I was just kind of throwing a lot at you. I think the thing to take away is we've also been trying to think of what we can do to kind of push the field forward, coming from our experiences, kind of working with these data sets. IceChunk is a big part of it. What's on the horizon is IceChunk requires some level of homogeneity, so you can kind of stack things together in dimensions. This doesn't work so well for everything. We're definitely lacking more on cross-language bindings. We have Rust, Python, a little bit of JavaScript and TypeScript today. We should definitely do more. What we haven't done yet are schemas, so that's the one thing we want to steal from databases. Updates are kind of hard to get right in today's Python stack with this, and I personally don't like best practices. We need like enforcement just to avoid errors. Like these data sets are so big, you have to be very careful. And just zooming out, like what's missing, right? We think we've built an extremely good storage layer. And we think the lesson from databases is that close cooperation between the storage and compute layers unlocks quite a bit. And we think the Earth system, the Earth sciences is just missing all of these concepts, right? Most scientists have no idea of things like incremental view maintenance, or things like derived fields that are kind of expressed as graphs on disk, and then you just compute them on the fly as you read them in, right? Things like streaming computes, like as was pointed out, satellite taking photos of the Earth is really a very slow stream of data, right? It's just an update every 30 minutes. Can we build like these updating data sets? And that's the kind of thing that I'm starting to think about now, and we're trying to like work on systems that can kind of get there. We have a very big batch compute framework. Is really how we've kind of operated for many years. Like you just crank through terabytes and you like save that, and then you analyze that, right? And so everyone kind of redoes this. And it's like, can we push the field towards a more incremental streaming view of things? I'm going to skip that last point because we're running out of time. So. The summary is that we thought we needed a new storage layer. IceChunk is that layer. We're all going to be talking about building new systems today. I hope I've made a strong case for IceChunk being the storage layer of that system. You can try it out today. I'm around. I'm happy to help. Things to take away, it smashes together a number of good ideas that we've had as kind of Earth science data systems people, as well as things that we're trying to steal from the database side. And I really view this as helping increase engineering rigor in kind of the Earth data ecosystem, and it's a thing that we've needed, and a bunch of us feel that it's been limiting us for a very long time. So I'll stop there. Thank you.
One question. There's a bunch of questions on the
okay.
doc as well, which you can look at. Like there's like 6 or 7 questions.
You want to like go and just like write answers in the doc.
Yeah.
I can do that. Yeah.
Let's take a question from the room. Yeah. Go ahead.
So you mentioned incremental view maintenance up there, and I apologize if I missed this, but I didn't quite register places where you were actually say ingesting a query of some sort, processing a bunch of data, and then streaming out results from
yeah.
data.
Right.
How does that work?
You didn't miss anything. I didn't talk about it. It was too much to talk about, so I talked only about the storage layer. Today, that kind of stuff happens on a very ad hoc basis. So like a bucket notification lands, it triggers a Lambda, and then the Lambda tries to figure out how the state of the system changed and stuff, right? With IceChunk, we've given you a primitive now, so you can query the ancestry, or it's like the Git history of your data set. You can see this was my latest commit, this is what changed in that commit, and now I'm smarter about what changes I need to run. But it's still very ad hoc. What we're trying to do over the next year or so is build something that is much smarter and like understands like this bit of the data set has changed. Given this compute graph, this implies this change, and I need to run it. Yes. Today, all of that is bespoke, and everyone handles it on their own. And we are trying to come up with ways of making that better. And so I'm really interested in learning from you guys on how to build this kind of thing, and like what are good ideas for doing it.
Sounds like a very interesting project.
Yeah, absolutely. Thanks.
Awesome. Let's go to the coffee break. I'm sure there's lots more questions. I mean, there's tons of questions.
Yeah.
So we can have a deeper later with all those.
Good.
So we'll be back at 10:40.
first off, this is not just the work of myself, but actually a couple of different large consortiums. So we have this DJ for Earth collaboration, where we actually just recently got a paper published at the Journal of Atmospheric Modeling, as well as a even larger consortium of folks where we had a recent submission to the Gordon Bell for Climate Science. Hopefully get to the next round. Nevertheless, like at this point, I think there's like more than 50 people across basically every continent, from academia, national labs, industry, and sort of beyond. To sort of begin with, I want to introduce a couple of the sort of key challenges that at least I see when doing sort of modern Earth systems modeling. So the first of which is scale. So these types of simulations are extremely big and detailed. And by detail, I mean in both the sort of resolution. So we have consequently like a grid, and as we increase the resolution, the number of grid points grows quite large. So we have this axis, but we also sort of have a feature axis as well. We want to have an increasing complexity of the actual simulations that we want to do. Regardless of the sort of source of that detail, this creates vast amounts of output. As an example, for some amounts of simulations like this CMP6, we have like 10 petabytes of outputs. If you're just to look at, say, like an Arctic simulation, not even the sort of like whole world, at 1 to 2 kilometer resolution, that takes 7 million core hours, creates another petabyte of output, and runs on 10,000 cores. And I will note that 1 to 2 kilometer output is it's nice, but people nowadays are trying to do like 200 meter output, and obviously that goes up by the square plus. Another sort of interesting thing that I'll note here, which is useful for potential future data layouts we may want to exploit. I usually see this as sort of like a pancake Earth. So we have this image here on the top, where we have like an x-axis and a y-axis, sort of like going around the globe for this ocean. But the z-axis, the surface of the Earth, even the atmosphere of the ocean, isn't nearly as big as the entire circumference of the Earth. So we have this simultaneous notion that two of these axes are a lot more important than this other axis in practice. We also have a challenge which is fundamentally that of the data itself. So here, I have shown a bunch of sensors off the coast of Japan. So it turned out, very unfortunately, there was a tsunami back in, I think, 2011 that took out a nuclear power plant. And this was quite bad. And people wanted to figure out a good way to have like an early warning system for these types of things in the future. So they put out like a bunch of buoys all across the coast of Japan to sort of measure exactly the sort of relative shift to the size of the ocean. Again, I'm not an oceanographer myself. I'm a compiler person, but to collect a myriad of different pieces of data such that they could be sort of reconstructed on the back end and go ahead and predict what is the likely sort of tsunami, give some amount of an early warning. But you'll note here, this doesn't cover the entire surface. It basically follows what is reasonable to sort of put out, both within a budget as well as sort of physical constraints of what we can do. There's actually a really fantastic paper that won the last year's Gordon Bell Prize at using some amount of sort of inverse modeling to figure out where to sort of put some of these pieces, as well as do some amount of early tsunami prediction. The third sort of these big challenges is the models themselves. So at a very high level here, I'm going to go ahead and describe how I see these models working. So first we have some initial conditions. So I'm going to initialize that state of the ocean and the lakes to whatever pieces of data that I have. Either maybe I got it from the earlier pieces of data, or I fill it in with some sort of approximation. I go ahead and from there, I want to go run some simulation on top of it. For some of these pieces, I know what I want to run. I have some physical equations, but it also turns out that in the real world, we don't know the physical equation we want to run for all of these pieces. Sometimes it's just parameterized, so we need to go figure out what the right parameter on top of a Taylor series or whatever else is. Other times, we don't even know what the right equation is, so we need to go ahead and figure this out. This combines itself with the idea that there's also boundary conditions. Like I go ahead and I might want to sort of have a cyclic boundary condition, or I might have something going ahead and touching the various continents or the lakes. Nevertheless, the big sort of takeaways here is for all of these individual pieces, there's a lot of stuff we don't know. We don't know exactly the initial conditions. We don't know exactly the insides of those parameters, let alone the equations themselves. And we have all these other sort of different types of things that influence the actual simulation themselves. It turns out that there's a couple of nice things that people can go ahead and use to sort of predict and resolve some of these uncertainties. Differentiability is one of these big, heavy-hitting tools. It enables powerful algorithms to go ahead and analyze these models, in particular to compute inverse problems. You can differentiate with respect to that boundary condition. You can explore the forcing sensitivities. You can differentiate with respect to those initial conditions. You can predict a forecast, differentiate with respect to those parameters, try to calibrate to the data, or even import that sort of sparse data, and even potentially go ahead and compute surrogate models. Finally, the last big challenge inside of these real-world or system models are the code. You know, there's a lot of really big code bases out there. Like MIT GCM, I earlier today went ahead and did like a source line of code check. It's 800,000 lines of Fortran, roughly. These are big codes developed by entire institutions like DOE, NASA, Max Planck, and the likes. They're made by experts in the scientific side of simulation, not as much experts on the computational front, though they do employ a lot of people who are experts in computer science as well. And what this means is that sweeping changes are hard. There's a story like a couple of decades ago, and I might be getting some of the individual pieces of it wrong, when like I think it was MIT GCM wanted to go add differentiability. And it turns out differentiability, very useful as I showed earlier, but also very invasive. They had to have a second copy of each one of their individual functions, that if someone changed the original function, they also need to make sure that they maintain that second differentiable form of it. And it turns out that making sure to maintain twice the amount of code for nice algorithms that you can do is very hard. So they eventually dropped it because that added maintenance burden stopped them from doing the science they actually wanted to do initially, and it wasn't worth it to them at the time. Nevertheless, we have these 4 big challenges. We have scale, we have data, we have models, we have code. We want to go ahead and run these things. So how can we actually fix these challenges? How can we make them work? What I'm going to claim here is like we want to actually go ahead and combine the domain scientists with the computational and computer scientists. But we want to go one step further. We want to ideally build a compiler to automate that sort of computational burden that otherwise is potentially plaguing the ability of these systems to move forward. I'm going to primarily talk about this in the context of 2 different things. I'm going to talk about this in the context of differentiability, in the context of performance portability. This is applicable to many other regimes as well, that ideally we want to build compilers to go ahead and integrate in. So differentiability, derivatives are fantastic tools. They're really key to both science and machine learning. If you're a science person, like is the context of this workshop here, it's useful for uncertainty quantification, any differential equation, and even sort of computing the floating point errors inside of your program. If you're an ML person, you've probably trained a neural network or seen Bayesian inference or a lot of these other sort of things. And these are all examples across different scientific domains of algorithms that require differentiation. What's really cool is these derivatives can be generated automatically from code. So I here have this simple ReLU3 function. I can perform a derivative and have this new function here on the right, which computes the corresponding derivative of it. Instead of having x cubed on that branch, I now have 3x squared. And unlike numerical approaches, automatic differentiation has a lot of nice advantages. First of all, if I were to numerically approximate it, I could say f prime of x is approximately f of x plus epsilon minus f of x for some epsilon. Of course, the real derivative is the limit as epsilon approaches 0. So if I have epsilon any bit non-zero, even 10 to the minus 200 or whatever else, I'm going to get some amount of theoretical error because it's not exactly 0. Very unfortunately, I also get numerical error from the other side. If epsilon is really small, then f of x plus epsilon is very close to f of x, which means it might only differ in the last bit, or perhaps not even any bits, which means that we have both of these sort of regimes causing numerical errors from different directions. Even worse, let alone the numeric sort of error, there's also a performance question here. If I'm going to compute this and I want to compute the gradient oftentimes, so that's the derivative with respect to all inputs, I need to iterate through all of my inputs and then do this relative subtraction. One of the nice advantages about automatic differentiation is we can ignore these sources of numerical error, because like we see on the top, we're computing the equation itself, and also we can compute the entire gradient in one sweep. We don't have to do it for all of these individual inputs. Now, again, derivatives, really useful, but they're also very costly, and some of the most difficult to use algorithms, as we saw earlier. So I also work very closely with the folks who make these pretty pictures of black holes that get on all the newspapers. This particular one took roughly a week on a cluster to go ahead and run. Majority runtime is inside of the derivative, computing Bayesian inference. Fortunately, we were able to take this derivative time down to 1 hour on a single thread, and as I'll sort of joke, you give the computational science all these wonderful speedups, and it's really a currency that they used to do even more and bigger computational science with the original budget that they had. Same thing sort of applies here. There's a lot of different approaches that people have done in the past. There's, design a new domain-specific language. Now, this is great if your new DSL matches exactly the types of things that you want to do. So if you're a machine learning person, go write it in, TensorFlow or PyTorch. If you're a graphics person, put it inside of Tachi. Now, if it doesn't match, you have a little bit of a problem. First of all, it may not be able to run, or it runs really slow. So here we have the ReLU3 function. TensorFlow doesn't really like the idea of conditionals. It turns out you can sort of shove it inside of these lambda capture expressions, but it's not going to work out terribly great. Second approach is known as operator overloading. So inside of an entirely new DSL, I'm going to have a differentiable version of specific language constructs. Inside of C++, there's a tool called adept. Instead of having my regular doubles, I have differentiable or adjoint A doubles. Inside of Python, there's a tool called jax. Instead of calling numpy.sum, I'm going to call jax.numpy.sum for everything. We can go ahead and rewrite our code. Now it's going to take the templated version, so we take any type of double. If I want to go ahead and execute it, what actually happens is at this first x is greater than 0, I'm going to log the fact that I computed x is greater than 0. Then in the second version, when I compute pow, I'm going to log the fact that I computed pow. Then in my stack of instructions, I'm going to go ahead and one by one reverse interpret and compute the derivative of all the different things that I've seen. Now, this works, but it comes with a caveat. Interpreting instructions is a lot slower than directly executing instructions. Also, if we have a for loop here, and we just add a bunch of things inside of our stack, we now no longer have the for loop. We have just a giant set of all these sort of pieces. Third approach is known as source rewriting. Instead of making a new language or a new subset of a language, I want to take the existing code. I want to rewrite it and have it spit out new source code for me. There's a state-of-the-art tool for this called Tapenade. It's primarily in Fortran, but it also works inside of C. We take in ReLU3 goal. I want to spit out new grad ReLU3 as an individual function. Looks great. Looks like what I'd go ahead and directly execute. Equally comes with a caveat. That tool inside the middle needs to understand the entirety of the program semantics of the language given to it. And it turns out that the C++ language specification is very long. It's hundreds of pages. Nobody should read it, and most compilers even don't fully implement it, let alone an extra tool. So if you have pointers, you have templates, you have structs, you have any of these sort of things that aren't even terribly crazy in the context, these tools often don't fully implement it, and then you're sort of yet again stuck in being able to not differentiate. But when it works great. All of these, independent of your favorite, because they all come with their own sets of pros and cons, follow the same general idea. I have source code in my favorite language. I spit it through an AD tool in my favorite language. I get new source code in that language. Then I run the compiler. And I run compiler optimizations, and I execute the final code. We can now look at how this actually works in practice. So when I was actually in undergrad, I was both a physics major and a CS major. So I spent all of my time normalizing vectors for fun. And I wrote this here as a physics major. So here we go ahead, magnitude costs O of n. This normalized function, though, costs O of n squared, because I compute magnitude inside the loop every iteration. Fortunate for freshman me, compilers exist, and they can figure out that we can move the magnitude function outside the loop, bringing down the total runtime to now just O of n. Now, if we want to differentiate this code, it basically involves running it backwards. So if I take the faster version of the code, I run the faster version of this backwards. I have grad mag outside the loop to begin with, or I have regular mag outside the loop to begin with. I have grad mag in the derivative loop outside to begin with, also runs in O of n. That's not how those existing tools work. Existing tools work the other direction. We have mag inside the loop, because we didn't run the optimization yet. We perform differentiation. We have grad mag also inside the loop. We can run, once again, loop invariant code motion, try to fix it up in post, but we get stuck. This, variable dres is defined in the loop. It's used in that grad mag. We can't hoist it outside. And the key idea here is if we can move differentiation to happen after optimization and combine with it, at least in this case, we can create asymptotically faster gradients and hopefully practically faster ones as well. And that's exactly what we're able to do. So we built Enzyme. It works on the compiler representation. In the first iteration, it works on LLVM. It now also works on MLIR. And whatever your favorite IR sort of is. Gives a couple of key benefits. One, we don't really care what source code language that you use. The production Clang, the production whatever else already emits all that front-end lowering for us. So we don't really need to care if the language spec isn't supported. We just need to implement differentiation on that internal level. And notably, we can combine with optimization as well, hopefully getting a little bit better performance and going to our favorite set of devices. As a quick example of how this works, I have that ReLU3 function. I have this enzyme autodiff, which is a magic function. In the LLVM world, the code appears here on the right. I have the branch. If I'm going to go ahead and execute it, conditionally execute pow, and if not, go ahead and have the final return. I first run an analysis known as activity analysis. I want to figure out which of the variables are important to differentiation and which ones are not. This is useful for two reasons. First of all, if we're going to avoid differentiating instruction that doesn't actually matter to the overall code, I save a lot of time. The second reason is, we saw earlier that the derivative of x cubed is 3x squared. Basic calculus. Can anyone here tell me what the derivative of thread ID is? Excellent. Yes. Yeah. Perfect from AP comes. Yeah. There's no really well-defined derivative. So we want to avoid taking derivatives of things that don't make sense either. And we run a whole analysis to figure out which we need to take derivatives of. For each of those original variables, we're going to allocate in zero what's referred to as shadow memory, so like space to store the derivative. And then for each one of those differentiable instructions, we're going to go ahead and compute what's referred to as an adjoint, or basically, we're going to increment the derivative by the partial. So in this case, increment it by 3x squared. We do this for all of the partial derivatives in our entire program. We get the total derivative. We successfully compute the entirety of the expression we care about. We can, of course, run optimizations in post, and we get something that looks relatively nice. And we're going to stop looking at LLVM now, and we get the equivalent to the high-level source code that I would have wanted to begin with. we can go ahead and run this on a bunch of applications, and we did this for our first paper at NeurIPS back in 2020 on both some scientific code as well as some machine learning code. And the sort of key idea we wanted to check here is how much of an impact does moving that differentiation to run after optimization actually matter? So in this enzyme and reference pipeline, in blue and orange respectively, they both run the same tool we have called enzyme, except for the enzyme pipeline, we run optimization first, whereas for the reference pipeline, we run differentiation immediately first to emulate as if it was implemented at the source code, just in case there's any differences in implementation between our tool and another tool. And that ablation test alone showed that moving differentiation got you a 4.2x speed up compared to not moving the differentiation procedure. Now that's very fun, but let's get back to climate science. So here we go ahead, and we want to go solve some interesting problems. So here we have what's referred to as the sort of shallow water equations. Effectively, it's a partial differential equation that describes basically Navier-Stokes. You start at some initial condition, you iterate forwards in time, and you time evolve it. And specifically here, we want to perform a sensitivity analysis. So how does some quantity change if I perturb the field? That particular quantity here represents kinetic energy based off of the individual momentums. I won't dive too much into the physics, but I promise we go run this and we get pretty pictures like shown here to compute the relative change of the sort of like logical quantity of interest with respect to the things we actually care about. That comes with some caveats though. Like I mentioned, we iterate this thing through time. So here is a very simplified version of iterating something through time. We might need to save data from each one of our forward iterations to be able to compute the corresponding derivative. If we're very lazy, we just save every single iteration, and then the amount of data we need to store is going to be proportional to the total number of iterations. This can quickly blow up, especially if you want to have a long time horizon running evaluation. And there's a lot of techniques known as checkpointing that try to perform algorithms to reduce this. Here I have a very simplified version of this, where effectively we save every few iterations, and in the backwards pass we just continue forwards a little bit from there. This is extremely useful in the climate and science domain, and actually an active area of research right now, figuring out how we can reduce this memory burden, because when you want to run big computations, you also want to run a really long time, usually. Turning on versus off checkpointing for the memory obviously changes the asymptotic behavior. So in blue, we have it relatively flat with respect to the original simulation versus just blowing up. But it doesn't also just impact memory, it also impacts the overall runtime, because if you're going to have to save and load and store more into memory, that takes time. So potentially counterintuitively, this saves both memory and execution time by performing the checkpointing, at least in this case here. The second big problem that I alluded to is differentiation is useful, but also there's been a lot of trends in computing hardware recently. Here, I just screenshot a bunch of examples from, Meta, from Anthropic, from AWS, from Google, all saying they have the latest and greatest AI chip, which is very fun. But these AI chips are not designed for existing code, let alone the sort of scientific computing or sort of even more general, specifically the like climate modeling that we want to do. They're designed to speed up the AI models. And in fact, they claim, at least Google does here, that there's more than 24 times the amount of computation in a single pod of TPUs than is available in the largest supercomputer in the world. Now that's great if you're an AI practitioner, but how do I access these chips? And for just ease, I'm going to put an asterisk here and write all of these as TPUs. Google was the first to really create one of these tensor accelerators. They called it a TPU. Everyone else has their own name for this. You have like tensor cores on GPUs. You have like Mida from like Meta and whatever else. I'm just going to call them all TPUs and put an asterisk on it. And scientists, unfortunately, do not write code which is friendly to these TPUs. Here's an example snippet from MFEM, which is actually what was used in that Gordon Bell run earlier, not our Gordon Bell run, but the one for the tsunamis, as an example. MFEM, once again, like the other climate models that we were talking about earlier, is also very big, hundreds of thousands of lines of code. It's templated. It's, most importantly, not inside of Python to be able to make this go ahead and run there. It's sometimes in CUDA. But if we look more deeply at some of the scientific code, and specifically if we look more deeply at the types of code inside of climate models, there's actually a lot of structure here. So here's how, from a state-of-the-art model called Oceananigans, implements all of their sort of like, forward models inside of Julia. It looks like just a bunch of generic CUDA kernels. I will save you the Julia syntax, but we call this arbitrary kernel twice. If we step back a little bit and we squint at what that kernel is actually doing, it's basically running a convolution across the entirety of it. And this is actually extremely interesting because those AI chips were first designed and implemented back in 2017. And if you look at AI in 2017, convolutional neural networks were all the rage. And it really does take a long time to go tape out chips and send them off to the fabs. Fortunately for all the AI folks, those convolutions are actually, if you build a good convolution machine, it's also usually a good matmul machine, and that same matmul is exactly the sort of process inside of the big sort of transformers that we go ahead and run. But in a little bit of an odd change of fate, the very sort of accelerators designed to go ahead and speed up AI actually, could be argued to be even better for the scientific codes here that we care about, if only we could get them onto those chips. So that's exactly what we went ahead and we aimed to do. So we built a framer that was designed to take existing code, in particular in this case, existing CUDA code, as emitted by your favorite compiler into LLVM, and raise it up to the high-level tensor instructions that are available within these chips. So we go in multiple stages. We first have our front end. In this case, on the right, we show Julia. It emits LLVM code. We raise it up to a high-level form that has generic forms of the parallelism. I'm skipping over a couple of the details. From the high-level form of parallelism, we turn it into high-level tensor instructions, perhaps not the fastest tensor instructions, but one that at least run. And then we go ahead and optimize those tensor instructions to make it one that we actually do want to execute. And notably, from here, we're able to take a single node version of the CUDA code, which is even better, because then the sort of domain scientist doesn't need to think about how to distribute their workload across these individual pieces, and automatically synthesize a distributed, either GPU or distributed TPU, or your favorite version of the program. So we work in several in several steps. So we start off with the original LLVM code is imported now into MLAR. We detect the high-level structure that this represents, mathematically an absolute value, that this represents not just, an individual sort of go-to style block, but a while loop. From there, it represents a for loop. From there, it represents an affine or sort of known memory accesses inside of the for loop. All that's very fun. That's covered in some earlier papers we have on a tool called Polygeist, published at CGO and PPOP a couple of years back. I'm going to focus on this last step here, which is how do we get that final piece to the tensor instruction set? How do we get from there to stable HLO? It turns out that representing your program as a sort of permissive or device-agnostic form of parallelism is incredibly powerful. And again, if you're interested in more details on this, email me and I'll forward you the relevant papers. But we've now raised this to a form that we have a generic parallel for that doesn't care about what device, and just says it is legal to run in parallel, not that it is required to run in parallel. So one way we can go ahead and execute this parallel loop is we can run iteration 1 fully, then iteration 2, or maybe even iteration 2 fully, then iteration 1. We can also interleave the individual instructions inside of this loop. So we could say run all of the load instructions across all iterations before we run any of the sign instructions across all iterations. It turns out that style of lockstep execution is so useful, we're going to go ahead and do it. So we're going to actually go ahead and execute all of the loads across all of the iterations of the parallel for loop, and we're going to form that into a tensorized version of the slice. We go ahead now and we run all the iterations form of the sort of sign instruction. We have now a tensorized version of the sign. We keep doing this through all of the instructions in our original program, and we are able to generate a sort of tensorized version of our original CUDA kernels. Caveat, those original tensorized versions of the kernels are not necessarily the forms that you actually want to go ahead and run. So if we take that stencil kernel to begin with, I have those overlapping adds, or rather the overlapping loads that we multiply and add up together. That is not the convolution that I was promised and makes us run fast on the chip. But it turns out if you build a bunch of linear algebra optimizations on this high-level form, we can actually detect and turn this into a much better form of these tensor instructions. And we have a paper back at last year's UPSLA where we, in fact, even combined with egraphs to figure out the best search through this sort of linear algebra space to turn into the fastest form of the tensor instruction set. We can go ahead and run this, and we actually get very nice, pretty pictures. Not only do we get pretty pictures of the primal, but we also have the derivative. So here's actually, once again, computing the sensitivities now on, big, Earth models. And I forget which one is an atmosphere and which one is an ocean, but we have one of both. We ran this on very big sets of machines. We ran it on, thousands of GPUs on Alps. So we had like 9,000 GPUs, at 4 per node. We ran on the DOE machine, as well as, 8,000 of those Google TPUs that together claim to have, 46 exaflops, though with a big asterisk on the number of exaflops of FP8. Before we go ahead and say, did we take the single node version of the code and successfully run it on the big version, it doesn't really make sense to go run on 1,000 chips if you're 1,000 times slower on one chip. So we want to double check that we're still, even through all this crazy nonsense, having a relatively good version of our code. And at least for the single node CPU code, before all of the tensor optimizations on this climate model, it ran in 272 seconds. With all these tensor optimizations, we bring it down to 11.5 seconds. So it's even faster for the single core. So probably we'll get some good results when we go and change it to the multi-core. So here we have the sort of weak scaling tests across GPUs for both the ocean and the atmosphere, respectively. What's shown here is the sort of time per grid point. In a weak scaling test like here, the basic idea is that you want to go ahead and have, you increase the resolution. So each GPU has the same number of grid points it needs to go ahead and compute. So the ideal scaling here is that it takes the same amount of time to go ahead and run each one of these individual pieces. So of course, in practice, it won't necessarily take the same amount of time. You might have some communication between individual GPUs and the likes. Fortunately for us here, we show that we are able to scale nearly perfectly. There are some blips and other stuff that I'll talk about a little bit later. We can also go ahead and run on the TPUs, like promised. At peak from this, we managed to go ahead and we used 97% of the overall TPU cluster, which itself contained 36 FP8 exaflops. In total, we used like almost a petabyte and a half of HBM to go ahead and store the fields. There are some extra caveats here that we didn't fully fix in some distributed optimizations that I'll mention in a second. These chips have registers that are not just individual floats, but like a sort of like vector of like an 8 by 128 individual floats. Same weak scaling is relatively good. We do have like that 8x there. On the one TPU, we get still the good sort of 40% plus of the runtime used in the computation, though again, we'd have some amount of an overhead. To give a little bit more detail on that, there's a lot of extra work that I won't have time to go into much detail on that is required to make this go ahead and run efficiently beyond just the linear algebra optimizations. As an example, we also had to build a whole host of distributed specific optimizations. So, if you're slicing all these overlapping pieces, you're sending data left, we really want to, as an example, do a common sub-expression elimination to, avoid sending the same data multiple times, as an example. Or another sort of example of this, if you slice off just the first element, because you're setting up a boundary condition, and you're copying that to the start or second guy, you're now taking a 100 by F32 tensor into a 1 by F32 tensor. And the sort of default way of doing this inside of something known as sharding here is say I have 10 devices for my 100 elements. I'm going to give 10 elements per each device. But now when I have one element for this intermediate tensor, how do I divide one element amongst 10 devices? You end up with like an all gather, and that's quite bad. It turns out we can do some notion of sort of like a communication fusion to get rid of it. And if we compare running these communication optimizations at the top right here versus not running these communication optimizations, we get an order of magnitude speed up. There's equally interesting questions here. How do we actually use the low precision arithmetic on side of this? If you're interested in the low precision parts, we have a couple of papers both at CGO last year as well as SC, and even later today, one of my students will be giving a talk at the eGraphs workshop on automatically leveraging low precision through arithmetic rewriting and the likes. So in total, Earth system models really have these 4 key challenges: scale, data, model, and code. The argument that I'm trying to at least make here is compilers are a promising route that we can automatically resolve all 4 of these challenges without the domain scientist needing to become an expert computer scientist. We demonstrate this in promising regimes for both differentiation with our tool enzyme, as well as performance portability with our tool reactant. And both tools work generically across LLVM/MLIR, all open source. There's plenty more problems than the ones that I sort of mentioned here that we've already started to explore with compilers that are extremely relevant to the Earth system and general community. And if you're interested, please reach out. Thank you so much.
So, thanks so much for that talk. Loads of awesome stuff. I wondered about sort of the relationship with things like JAX, so the stable HLOs like compiling to TPUs. How would you compare that with an approach like JAX, which sounds roughly similar?
Yeah, so JAX also converts Python into that stable HLO representation. Caveat, by not being directly inside of the compiler, it presents some additional limitations through tracing. Like, you don't have direct access to for loops, you don't have mutation, so there's like the sort of the language level from there. Independent of the language level, there's also the question of like, how do you make sure that the performance from stable HLO to machine is actually fast? So all of these optimizations we did, say, for improving distributed performance, improving numeric performance, all of these equally apply to JAX code. So you can take your existing JAX or system model, take these extra optimizations with a flag I can recommend to you, and you should be able to fix a lot of these sort of things in that regime as well.
So your argument here is that a scientist shouldn't have to think about optimizing these things. They can write these Julia kernels more or less normally.
Yeah, so the ideal here is that you write kernels in Julia or C++ or whatever else as you normally would have specified, which tells the compiler it's legal to run in parallel, and we want to convert this automatically into a form that is efficient to run across all of these devices. And it turns out that the efficiency part is hard, but fortunately that's exactly what compilers are good at doing.
Yeah. Maybe you can take one more question while.
Yeah, oh, sorry.
You still have some remaining code in the original language, like for Gen C?
Easy? Yeah, great. So actually, I'm going to go back for a second and start with this slide before I forget. My program director asked me to show this. I partly work at ICCS, the Institute of Computing for Climate Science at the University of Cambridge, and we're organizing this sort of online hackathon aligned with this thing called Hacktoberfest I think it's in October. And it's a chance where you could kind of get together with people who do programming in science, collaborate with people on open source software projects in climate science. So if this is of interest, take a look. We've got some sort of information. You can get that here. So I'll just leave that for a second. It's an event that we're running later this year. Okay, so on with my talk, and thanks to all of these people who are listed on the slide, sort of people I work with. This is like a position paper, as it were, like a kind of, that's why I wrote it in this way. This kind of position that I'm putting forwards is that general purpose programming languages impede scientific model development and communication. This is my position, and I'm going to talk about some possible ways forward and also show a work in progress kind of solution that might, towards this kind of solving this problem in this space. So thanks to all of my colleagues here for sort of conversations and work on this idea. So I want to start with this idea that code is really about communication. Okay, we could primarily say it's like communicating with the computer, but it's also how we communicate amongst ourselves as humans. And so in the past, when people did science, they used mathematics as the kind of central language of describing models, or at least, let's say, kind of from the kind of scientific revolution sort of onwards. So you'd write down some equations that would kind of capture this physical behavior, and maths is really, really good at that. But now, our models are these very large piles of code, and actually there's so much sort of detail in there that gets embedded in the code that really the sort of model that we want to communicate now is okay, there's some mathematical equations, but it's also the whole code as well. And we've seen discussions already about the scale. You know, we're talking for things like Earth system models can be up into the sort of close to 1 million or a couple of million lines of code, and even smaller models, they can still be rather large and difficult beasts to understand. We've also talked about FAIR earlier, so Cyrus had a nice discussion of that. There's been loads of great progress in recent decades about I guess kind of socio-technical progress about the fact that we need to have our code be open so that people can actually use it, and based on these FAIR principles. So it's not just enough to have the papers that describe what's going on, but you also really need to share the code, because that's where the actual key parts of your scholarship are in the actual model that you want to put forward of whatever processes you're looking at. But then we have some problems that come with this. You know, sharing the code is great, but it doesn't sort of solve the problem of how we communicate about the science that we're doing, and one of the things that kind of works against us is the inherent complexity and the accidental complexity. Now, the inherent complexity we can't get rid of. You know, that's there in the things that we're modeling. And what we want from our programming tools and the things we're doing is to kind of illuminate what's going on in the inherent complexity, and then avoid all of this accidental complexity. So when we write down the code, we have to make all of these choices about how to run it efficiently and how to kind of plug into all of our systems, and that starts to complicate the code. And you know, a long time ago, I was writing sort of data parallel fluid simulations, and it's like you basically just have to rewrite the code every time that you want it to target a different architecture. And so there's all of this accidental complexity getting in your way. So we want to avoid that. A bunch of kind of experiences that are kind of informing some of the things I'm going to talk about today came from a collaboration we had with actually some people here at NCAR, up the hill at the Mesa Lab, and various folks around the world, where we were looking at moving a data-driven subgrid model, one of these parameterizations, moving it from one particular atmospheric model called SAM into the community atmospheric model, which is part of CESM. And the kind of idea was like we had to take this paper and the code that came with it. It was a sort of neural network parameterization. It was part of SAM, but it was kind of written in a way that it was like too heavily embedded into that piece of code. And where the starting point was like, oh yeah, we should just be able to sort of yoink it out and put it into this other model. But as we kind of all know, it's not so straightforward to do that. We had to sort of really re-architect this. And when I say we, it was really Jack was doing a lot of this work. He's a principal research software engineer at ICCS. And so he re-architected it into these kind of really well-defined layers with well-defined interfaces so that you could sort of take out this middle bit and then move that over to CAM, and then write this kind of CAM interface to the data-driven model here. But doing that was also very difficult and required a lot of interaction with the people who'd written the original paper and with the sort of scientists and the folk at CESM who were the folk at NCAR who work on CESM. They were super helpful. But there was a lot of this kind of, what does this variable mean? What are its units? What's its resolution? Does it mean, is this a change? Is this a tendency? Is this an offset? Things like that. So there's a lot of kind of understanding what the code actually does, and it sort of didn't really describe itself in a way that helped us do that work. So that kind of experience, Jack and I have then spent lots of time talking about what are the right kind of software engineering principles that would have helped avoid this situation. I think this is kind of what I like to call the semantic gap. It's emblematic of this kind of gap that we get between our papers and our code. The papers get written, they have the nice equations in them, some abstract model. Then we have to do some discretization, some numerical analysis, and then write a load of code over here. But then there's a sort of gap that opens up between the two, and they become sort of decoupled. And our programs often sort of throw away a lot of the original abstract ideas. The abstract ideas we put in the paper don't describe the code, and we get this gap that then kind of impedes our scientific work. So this is the mind the gap is like a classic thing in the UK when you're getting on the train, and they always say, please mind the gap. I think my colleague Rowley has this really pithy thing. He actually said this on Friday in a meeting, and I was like, yes, this is really it. He said, treat the code as your knowledge base. When you have knowledge, serialize it into the code. And I think this is something that we can sort of aspire to if the code is then this kind of central place in which we discuss the scientific work and kind of can also unite around across different disciplines. Like, it's great to have lots of different disciplines here today, and like one of the places we can kind of communicate is via the code. But how do we do this, right? And so I think the contention in this position talk and paper is that our programming languages don't really help us to do this very much at the moment. They're like too general purpose. And general purpose is good. I can take Python, I can do loads of stuff with it, which is brilliant. But then when I want to do science with it, it's sort of that generality can work against me. So how do we close the gap at the moment? This is the bridge in my college that goes from the old side to the new side. It crosses the chasm. It lets us bridge between worlds, so a bridge between two different places. How do we bridge between this semantic gap at the moment, between our kind of scientific ideas and our code? Well, one thing we've kind of talked a bit about already is naming. And names are good, right? But then, you write some code and you get things like this. This is I think this comes from the convection parameterization thing I was mentioning earlier. And you sort of look at it and go, what does this mean? This is like absolute temperature, and this is maybe temperature, and what is this thing? And they're some real arrays in Fortran. This is like a classic thing that I'm always telling my students, write variable names that actually describe what's going on. And then, of course, I go and write code where they're called things like A, B, X, and Y, right? So from the programming language point of view, from the language semantics, names have no semantics, they have no meaning. Like in the programming language world, we have this idea of alpha equality. Like if I say I have a function that takes in an input X and returns it, it's the same as the function that takes in Y and returns it. But actually, names are really helpful to humans and maybe also to things like LLMs. And we had this, I rewrote my slide earlier based on the Deepak's talk before, where he made this point about in Xarray, the really nice thing about Xarray is you can actually name the dimensions in your metadata rather than saying like x-axis is 0, which you can't remember. So lots of things, lots of developments that exist have kind of pushed us towards actually describing what's going on in the domain in the code. So Xarray is good for that in Python. But often we can kind of get into this situation with like very long kind of naming about things. And one of the problems is that names are, they're not compositional. So we mentioned, so this was, I also stole this from the talk as well, right? Like this is a kind of, it's a name that's been just put together by like string concatenation, but it sort of then has no structure, and it's hard to connect us back to where it came from. And also, it is hard to name things as well because you have to then have some sort of agreed set of names, and often the names are like different in different places. So you might get like sea surface height from an oceanography point of view, and then like water level from hydrology. These might actually be the same thing, so you need to sort of deal with different communities. And CF conventions got mentioned before. This is like a really great, I think this is like a success in the sort of space of you sit down and as a community you kind of come up with a naming scheme for things. But then those names do get very long and very complicated, and they're not very compositional, they don't have any structure. So you get sort of these like very long names for things like atmosphere, absorption, optical thickness due to black carbon ambient aerosol, and then you've got one that's about due to dust ambient aerosol particles. And the naming is good because it helps us kind of then explain what variables mean, but they're not decomposable, and you can't build them up from smaller components. Okay, comments, right? Comments are really important, and like documentation in general. But the problem is it's second class, it doesn't have any semantics, it kind of gets thrown away by your compiler, thrown away by the language, doesn't really exist from the sort of actual meaning of the program, largely. It doesn't have any structure, it ages like bread, it goes stale, or like milk, it goes sour, and so it's sort of decoupled from your actual code. And I remember a conversation I had probably about 20 years ago with some scientists, and we were looking at their code that had units of measure in it. And I said, oh, this is really nice. You got the units of measure for each variable. And then the postdoc was like, oh, no, that one's wrong. Oh, no, that's not that anymore. It's like it had just kind of gone out of date. There are nice, like fancy kind of tools that help us extract documentation from comments, things like Sphinx and Ford and Doxygen. These are all super helpful. They like surface our comments to us in a structured way. Doc strings are an interesting thing in Python because they do actually have some computational meaning. They're not like purely a comment. So we can do things with these kind of richer commenting structures. And just a like a really nice example from some of our collaborators. This is a eco-optimality model of plant primary production. They have really nice documentation that has like maths in it, and it generates these really nice docs. Like this sort of stuff is great, and the comments are there with the code, which I think is largely a good thing. But then, this can easily get out of date with actually what the model is doing, because there's no connection between them. Just a mention of something that we've worked on recently. So Fluid is this programming language that Rolly Pereira is one of the, he's an early career advanced fellow at our institute, and it's a really cool language for building visualizations that are automatically explorable. He's talked about it at previous PROPLs, and we've just added this feature called literate execution. So you have this kind of comment that you can put in the code, and then when you execute the program, that gets sort of interpolated into extra explanation that comes with the execution of the program, with like spliced in values. So, okay, it's a little bit hard to digest this. Sorry, this is just a grab from the paper, but this is a kind of output you get from Fluid, and you can click on a bit of the output here, and it brings up the input from which is computed, and this comment here, this kind of special comment syntax, generates this extra information here that comes along with the execution, sort of explain how the computation has been done. So we use the term literate execution to be, it's like we're executing, but we're like explaining how that was produced automatically. So we just had a recent paper about that. I don't want to talk too much about notebooks. We had an interesting discussion about that before. Like the idea of literate programming is you like write lots of comments, and you could see notebooks as an evolution of that. I think there are a lot of problems. Like notebooks are great, and they have done some really cool things for the community. But I have observed, and as many of others, and Cyrus talked about this, they do become very monolithic and not very modular. They don't guide people towards like well-modularized bits of reusable software. And lots of problems with like execution order and state persistence and so on. So one thing I'm very keen on, my collaborators know, is trying to have like single source of truth techniques, where you have like one way of describing something from which you generate multiple artifacts, so that you're not having like the paper says this and the code says this and the documentation says this and so on and so forth. A kind of way of closing this gap is to try and have some kind of representations, like single source of truth representations, from which you generate lots of stuff, so you only have to change one place and these things don't become out of sync. And there are lots of examples of this around the place. Project that we were doing internally was to do with looking at sort of optimal, the kind of Pareto optimal frontier of land use in the UK between sort of forests and agriculture and all these kind of things. And Robert Rouse, who I should mention on here, who's worked on this, he has this really nice kind of dashboard and all of this cool genetic algorithm stuff for doing this modeling. And one of the things I was looking at when we were doing this work is saying, well, you have all of these equations that are like constraints on your model, and they kind of get replicated in lots of different places. They're like described in the paper, they're in the code in order to constrain the genetic algorithm, but they're also in the code to constrain the dashboard that we produce as the output. What if we just described them once and then like generated all of these from that description? So we have like a deep embedded DSL for this. I'm not going to do a live demo because it will take too long, but you write some Python that describes these constraints between variables. You can't just like have the UK and make it all be forests and all be agriculture and all be houses as well. Like there has to be some constraints. We can't do it all at once. And this generates then constraints on the UI between these little sliders. So if you move the grassland up, then the organic regenerative farmland has to go down. It also constrains the genetic algorithms, and it also generates the LaTeX for the paper. So you just have one single format that's like a syntax tree essentially, and you generate all of the things from it. So that's trying to like close this gap, but in a very like we solve this problem in one place kind of situation. So you do get kind of approaches that are more about having structured comments, so things like doc tests. They're a kind of format where then these comments get read and they get turned into tests that like the automatic test suite will use. So that's really nice. It's like putting a little bit more into what the comments actually do, giving them some meaning by some external tools. You could also have comments that have some specifications in them that are then read by other tools. So this is something we did in the CamFort project, where we looked at building lightweight verification tools for Fortran. And we had things like units of measure typing. We have this in the tool. So this is Fortran code, but with comments that then the CamFort tool reads to do dimensional analysis checking on your code. So you can sort of run CamFort units check on this code, and it checks whether this is really supported. And you can do things like synthesize additional unit information into it. And the idea is that those comments are then, they have some meaning that's read by another tool. It doesn't interfere too much with the process of the rest of the scientists because they're still just comments. You don't have to run CamFort on them. But it's like trying to bring in some structure to those comments to, again, bring in some of that real domain information. Like, these are not just arrays of reals or reals. They actually relate some physics. So they should have some units, and we should be able to do a dimensional consistency. So there are lots of like partial solutions to bridge the gap. We could like work really hard on documentation, and we should do that. That's good. We should do some like clear systems design that kind of reflects the science and try and think about, okay, can we build things that are modular, that are sort of like kind of well described. This is good. This is sort of basically sort of saying people should put more effort in software engineering. And I think we're going to hear like a talk in the next talk, which will give us a sort of like maybe an approach to thinking about how we make models more modular, and like one way of doing that. But because my background is programming language design, it's sort of, well, could we have programming languages that help us do this better? What could it look like to have a language that's sort of pushing us in this direction to bring that domain information to our program? So, okay, going back to this, we want to sort of avoid this situation where we just kind of have these big real arrays of things. What if we could sort of bring more of that kind of information about what things actually mean into the language? And so I'm going to sort of break cover a little bit today. PROPL seems like a nice place to do it, and announce a language that we've been working on. It's a prototype research language at the moment called Fortl, but it's kind of designed to be descriptive and sort of maximally descriptive for doing sort of domain-specific modeling, or also perhaps prescriptive as well, because it has static checking, so it sort of forces you to commit to the interfaces you've designed. So I'm going to give, so it's statically typed. We have this way of indexing types like floats with additional information in a very lightweight way that you can sort of keep adding more and more and more and more information into the types. So the kind of float type, a little bit of type notation here, it's a sort of index type, so it expects to know about some descriptor structure, G, and then it also has this bit of information X which lives inside of G, so G is a type of descriptions, and associated to float we should then have an actual description X that lives in that G, and then that produces a type. And it's Python-like, so we can lower the barrier to entry, and maybe this is sort of what we're thinking of it as like one of these kind of orchestration languages. We're not necessarily saying like yet like we want this to be the orchestration language, but it's a playground for some ideas. Okay, so I can do a very quick demo of the very kind of early release. And this is not mirrored, so this is going to be okay, let me just switch to mirroring, sorry. Bear with me.
You're brave, Dominic.
Thank you. Yeah, Okay, there we go. Okay, so here's a really simple Fortl program. It looks like Python, right? X, Y, T, and it runs. At the moment, this is just floating point, but with not any extra information. But then we can start attaching information to this, saying, for example, that X is a float, and it has units, meters. Okay, here's another float that's also unit meters. Here's a float that's unit seconds. Okay, let's reload this. So this is a bit like the kind of Python REPL, but it's got some typing going on there as well. And so it's inferred that the type is, it's a float, and its description is a unit of measure, and that unit is meters per second squared. Okay, it's calculated it in that order, seconds to the -1 times meters. And that's fine. And if I had something else like here, where, I don't know, I put miles instead, then we get a type error saying, like, hey, oh, it says it twice, you know, just so you get the message. You know, I expected this to be meters and miles, and you can't add them together. But okay, it's not just about units of measure, because sometimes you need to go beyond that. What about kinds of quantity to say, it's a meters thing, but it's actually a length? And we might need to distinguish multiple kinds of lengths, multiple kinds of meters things from each other. Let's do it like that, for example. So then we get some like additional information very smoothly. And if I came along and said, oh, this is a meters thing, but it's actually in an orthogonal dimension, maybe you can't add that. And you don't want to be able to add those things together, right? Because it's like a length and a height. They're in orthogonal bases. And so by adding this additional kind of quantity description, then this is prevented. So early days, but the idea is to be able to like very easily like add in more and more of these layers in a domain-specific way for what you're doing beyond just dimensional analysis. Maybe you want to be able to distinguish between the moist air constant and the dry air constant, right? They're both having the same effect in the equation of state, but they describe different states of the atmosphere, and so you might not want to mix them. So that could be another kind of layer that you put in, or maybe you're like chemical species. So like if you're doing biogeochemical modeling, you want that to be an additional bit of information. So it's all about being able to do this in like a very lightweight way, without sort of lots of big overhead. So that was the demo. There's a bunch of maths into how this is structured in the type system, which I'm not going to go into, but if you want to know about it, you can come and geek out with me about that. It's based on this idea of an abelian group graded field. And actually we have like a generalization to that as well. But roughly it's like you've got two floats with the same descriptor, that's fine. If you're multiplying them, then you're going to multiply descriptors. If you're dividing, you're going to use the reciprocal, and then there's a sort of casting relationship. So this is a kind of somewhat known idea, and we're using that to build the type system. Okay. So I've been thinking about this for a while. We had this position paper like more than 10 years ago where we were kind of thinking about this, and one of the roadmaps there was to think about sort of, there might be future cool languages we could do, but we should also talk to scientists now where they're at and sort of have an evolutionary approach. I think what we're trying to do with Fortl is look at like what could the future be like, how could we build such a system. Let's like take the idea that we could build better languages for science seriously. What might that be? Okay, so I'm going to stop there. I mentioned that already. I put the slide in case I forgot it. So thank you very much. I think I got about 3 minutes for questions.
Yeah. Okay.
Mm.
That was very interesting, the last part where you had the statically type with the Fortl.
Yep.
And you have the units in there, but oftentimes you don't know the units.
Mm.
You know, you may have, you know the units should be lengths, they should be meters, but you could run the model in centimeters.
Yeah, okay.
As long as they all jive.
Yeah.
Except for maybe some cases, like I'm thinking like using Mannings or something, which is parallel relationships with kind of coefficients that have to be exact.
Yep.
How does it deal with that?
Yeah, that's a really great question. So it's sort of like, what do you do if you don't know the units, or if you're like agnostic to them or something like that? So actually, I don't have it here in this one, but what we've been thinking about is being able to just talk about things like dimension length and not specify the unit. So that makes a lot more sense in the context of like a function that takes some input. So if you thought about like f equals ma, you could describe that as like okay, I take these two variables m and a and produce the force, but that could just be described at the dimensional level rather than a units of measure level. So we've been thinking about that in terms of having kind of like a hierarchy between these, what we call descriptors, where from like dimensionality, you could say, well, I can generate the SI version of this. So there's like a conversion from dimensions to units of measure, like the SI translation. But I should be able to describe things very generally that maybe only think about dimensionality. Like that would be possible in this system. And you also don't have to commit to this. Like you can just work with raw floats, or you could even, like in this example, we could go back to this version, but then actually remove the units. The units don't have to be there. We could think of it, and I should make this type check. Like that's fine. So you can kind of have like, oh, they're this kind of quantity, but we haven't committed to the units. So I think there are sort of, by having enough flexibility and some polymorphism and some of these kind of hierarchy things, that's where we're heading towards. But it's a great question, and we're definitely thinking about that.
And in this case, I guess it would be okay if it was quantity length times quantity height. That should.
Yeah, that would work. Yeah. And then you'd get the height length overlapsed kind of, yeah.
Thanks, Tom. Sorry.
Yeah.
Maybe building off this, but thinking the opposite direction. So sometimes models are intentionally non-dimensionalized before they get implemented in code. And so I'm wondering, how do you see that sort of, those sorts of programs fitting into this language, or is that like not the right thing to?
No, that's a great question. So what about things where you've like normalized them to be unitless, I think is what you're saying. So even if you normalize things to be unitless, you might still want to know about what does this thing kind of mean, and where's it come from. A good example of that, another example of that, I think, is ratios. Ratios are interesting because they're just unitless, right? And often we work with things like kilograms over kilograms in like atmospheric physics. We want to like look at like densities of things. But you want to distinguish that ratio from angles. Angles are another kind of ratio. So by having these, like, it's essentially like layering on these different dimensions, you can still have things where it's like, well, this is unitless, but it comes from this quantity, and it like has this meaning. So the idea with quantities is a bit like that. It's kind of like separate, could be related, but it can also be separate. So you could describe different kinds of ratio, even though they're all just unitless, but still be able to separate those out. Yeah. So I think the same would be true for like something that you'd deliberately normalize to be dimensionless.
Yeah, I know. I think the typical workflow might be doing the normalization in pen and paper and then in the code.
Yeah.
So I'm wondering if there's a different workflow that might.
Yeah, so I can, maybe there's like a program transformation or a higher order function way of thinking about that could be implemented in something like this. Yeah. Great, I think I better stop there and cede the floor to the next talk.
as Dominic had before, is we can do model coupling with a fairly simple set of functions. That's going to be the basic model interface. So I'm talking today with my colleagues Eric and Greg. They are actual geoscientists, and we are a part of an organization called CSDMS. And so I'd like to talk just a moment about CSDMS because it has some important context for what I'd like to talk about today. And there we go. All right, so I'm trying hard not to read my slides. All right, so CSDMS is a group of scientists who do Earth surface processes modeling. So the ologies that we cover here are things like geology, hydrology, lithology, glaciology. All right, so it's a quite broad and diverse set of disciplines. And these people are gathered together. We do things like modeling of processes. We have a community, and we also do a lot of education. You can see our website there as well. As a little secondary feature of CSDMS, even though the science is the first thing, we're also big on promoting open source software. This is something that didn't quite exist in this community as of like 10 or 15 years ago. So it's kind of undergoing a bit of a sea change, a bit of a revolution, if you will. We're also into things like best practices. So Cyrus mentioned, for example, the FAIR principles. These are things that we teach a lot of grad students coming up now within our community. All right, so I highlighted model coupling because this is kind of this is our special sauce. This is why NSF likes to fund us. And I want to draw a little distinction between like what Deepak was talking about and like what William was talking about. Whereas they had to deal with a lot of problems that are global in scale, we tend to deal with more local problems and more local modeling problems. And so we don't run into the same problems necessarily as what Deepak described, for example, with the large data sets, and what William described with like the speed of doing the processing. So this informs a little bit about where we're coming from with CSDMS and where we're coming from with model coupling. All right, so how do we do the model coupling? Well, the first aspect of this is the basic model interface. All right, so again, the basic model interface is just a set of functions that we apply to a model. I'm trying, again, hard not to look at my slide, but I also enjoy this because I've been thinking about trying to find a different one-sentence explanation for how we can do the basic model interface. And so I asked this on our forum last week, and a bunch of our colleagues responded, and we kind of formulated an answer together. So I enjoyed that. That was kind of fun. All right, so the basic model interface. Why? Why might this be useful to people? All right, so this is my wife's car. She lets me drive it. Actually, my wife has 2 cars. I have 0 cars. This is one of them. She lets me drive this one. So it's a 2013 Subaru Outback. If I get into the Subaru, I sit down in the driver's seat. There's a steering wheel. I can control where the car's going. There's an accelerator pedal. I can go fast. There's a brake pedal. I can stop it. There's a speedometer. I can figure out how fast I'm going. All right, so there are controls in this automobile. Now, if I had to move a sofa, I could go to Home Depot, for example, and rent a truck. And I bet that if I got into that truck, I would have the same set of controls. I would know how to operate it. I may never have seen that truck before, but I know that I would have a steering wheel, an accelerator pedal, and a speedometer. So I've benefited. I've benefited by some standardization in automobiles. Wouldn't it be nice if numerical models had this? So that rather than having to learn how to run, Wharf Hydro versus Delft 3D, for example, if we had a standardized interface for how models work. And this is what we're trying to solve with the basic model interface. All right, so I have some design principles. These are things that we had tried to adhere to when writing a BMI. There's a lot of words here. I'll try not to go through all of these, but I'll probably try to cover many of them. So the BMI is language agnostic. It doesn't matter what programming language you use. We can write a BMI for it. BMI is self-describing. These functions have nice names that you can see across languages. When implementing a BMI, we use basic data types in the languages and use standard language libraries. We want the BMI to be easy to implement by a coder, because we're asking people for something. If you wrote a model, for example, as a graduate student, we're asking you to do extra work, extra credit, by adding on BMI functions. So we want it to be easy for the implementer, usually at the cost for someone trying to use a BMI. As a riff on that, we think of BMIs being for machines. Maybe not as easy for people to use, but easier for machines to use. I love the Popeye principle, so I am what I am. All right, so BMIs just describe themselves. They don't have to describe other things, other libraries. There's also the Hollywood principle. I didn't put this here, but the Hollywood principle is, don't call me, I'll call you. So BMI only responds when it's addressed. It's not advertising itself. It's not broadcasting itself. BMI models, for example, are used in a framework, and we leave tasks for the framework. It's not intended for every model. Not every model can be BMI'd. And it's for model coupling, but not necessarily model-to-model coupling. We can also do data-to-model coupling. We can think of data sets as a model. Like I think of a netcdf file, for example. Individual slices in time would represent individual updates to a model, for example. BMI does not inject itself into a model, so it's independent. You can still run the model without the BMI. The BMI currently, by name, is minimal, but it's open to extensions. That's actually a current topic of work. Right, so where can you find more information about the basic model interface? We have some documentation, and I'm really proud of our documentation. I think it works really well. People have been able to add BMIs to their models without coming to me and Eric and Greg and asking, well, how do I do this? So they've been able to go just from the documentation. We also have a fairly recent paper, this is 2020, where we describe the current version of the BMI. We also have specifications or mappings and examples. So the BMI itself is abstract. We just list function names and what the inputs and outputs should be. We've taken this abstract BMI and made it slightly more concrete in that we've set mappings for different languages. So you can see common languages that are used within our set of disciplines. I should also mention that the community has made mappings in Julia, JavaScript, and Rust as well. These are the ones that we work on in-house. Each of these has a repository and an example as well. The examples were kind of fun to make. We tried to make all the examples of using basically the same models, like a two-dimensional heat equation solution, Dirichlet boundary conditions, a uniform rectilinear grid, 0 with a spike at somewhere in the domain. So it's kind of fun to implement the same model across different languages. The implementation, again, this is the hard part to sell to people because it takes a little bit of work. So there are about 30 functions. They fall into different categories, like controlling how the model runs, initializing, finalizing the model, getting information about variables, doing time stepping, getting values out from the model, setting values into the model. The nice thing is that not all functions need to be implemented. A lot of them are kind of trivial to write as well. So this is just a screen grab, obviously, from the documentation showing a list of the BMI functions. All right, so BMI is actually being used in the community, which is kind of exciting and gratifying, I guess. So I just want to show, I went to dimensions.ai to get the latest counts of references. The Hutton et al., that's the recent BMI paper. The Peckham et al. Papers where the concept of BMI and actually CSDMS were introduced, and so it's been around a little longer. And then Tucker et al. Like a kind of a review of CSDMS. It's a little more recent. One thing that was kind of fun is the Hutton et al. Paper. It made a comment that most of these citations are in the last couple of years, so it's getting more uptake, which is kind of fun and exciting. So BMI is being used in different places. So maybe the biggest thing, this is kind of cool, the NOAA Next Gen Modeling Framework is using the basic model interface as a foundational principle for all models that go into it. And so there's a recent paper where this is described. You can see other government agencies, other government institutions, as well as private companies are using the basic model interface as well. So it's getting some use. And as a matter of fact, it's getting more use than kind of Eric and I can handle. So for a long time, the basic model interface was just Eric and I talking and just thinking about what should go next. Considering it is getting some use, a few years ago, we wrote up some governance documents for the basic model interface. We based on the NumPy governments, which I thought was helpful. And so we have a council now with representatives actually from the institutions you saw on the last slide. And they help set and guide the development of the basic model interface with time. We also have institutional partners from these places as well. All right, so current work, we're looking at developing an extension framework. So right now, the basic model interface is, again, just these functions, but there are other things that we'd like to capture with the BMI that shouldn't go into the core of BMI. And so things like parallelism, which BMI doesn't support yet, would be one of them. Not all the models in our community are parallelized, and so we don't really need that. Geospatial data as well is another place. So places where it would be better as an extension rather than having people implement them. We are working, so under the guidance of the BMI Council, we are working towards a new release of BMI, a version 3 release. We're targeting that for the end of September 2027, which is basically when one of the current awards that we're on runs out. We're also going to have a journal article as well. My little diagram here is just a class diagram showing how we could do a geospatial expansion in Fortran. Okay, so in summary, the BMI is a set of functions that are external to a model code. They're intended to be straightforward to implement. They're a pathway to model coupling. And importantly, they're open source and community governed. Learn more at our documentation. All right, so with that, thank you. Any questions? Dominic?
Oh, yeah. Thanks so much, Mark, for this. So could you perhaps say a little bit about how it works when you're working across languages? Like, what's the technologies involved in that?
That's a good question. So this is something that we kind of defer with BMI. So the basic model interface, we use it for models written in one of the languages that we support. If we want to have, for example, a C model talk to a Fortran model, for example, we leave that for the framework. So for example, at CSDMS, we have one such modeling framework. We call this the Python modeling toolkit. And so that includes basically ways for us to to work across language. We basically wrap models written in these languages in Python and then have them talk to each other in Python. So it's to answer your question directly, it's a little bit outside the scope of BMI. We handle that in the framework instead.
But then yeah.
Sorry.
Yeah, thank you. That makes a lot of sense. I don't know if this is working again. Yeah, I think that kind of relates to what Cyrus was saying earlier about, you know, it's difficult to just say to someone, oh, you have to use this one language, but if we want to move towards these, like the fair playground, like having this way you can get things talking together, having something like the BMI is like a way of sort of, okay, you implement this interface, and then you can fit into a framework that then sort of Legos it together, I guess.
I mean, in a sense, to build on what Cyrus said, we're using Python as our orchestration language in our community.
Yeah. Great, thank you. Other questions? I'll bring the mic over to you.
Hi, thanks for the talk. I think I'm struggling a little bit to imagine. Let's say I'm a grad student and I want to hook up a couple of different models. I have my own. What is like an example case when I should say, yeah, I want to hook up into BMI and grab something else? Like how would I reason about that?
Sure. How about this? Let me give a little example. This is my sort of pad example, and let me know if this answers your question. So the way I envision this is that researcher A writes a model that transports sediment downstream in a river. Okay, so the output of that model is there's a sediment outflow, there's a discharge at the end. Researcher B, maybe at a different university, writes a model that creates a delta from sediment. All right, so these two models could be written in different languages, for example. But kind of what we do at CSDMS is we would provide the kind of the middle. So researcher A could put a BMI on their river model. Researcher B puts a BMI on their delta model. The output from the river model would be used as input for the delta model. And I want to be careful because just BMI alone is not sufficient. Again, this is where we need the framework that would allow the two BMI models to talk to each other to actually transfer the information. But having the BMI on each of the models is the first step in this process. And so maybe if I could take a step back and go a little further as well. This is something that was by design from CSDMS. The idea was that we would have all these people in CSDMS, in this community, everyone writes their own model, and then if they put a BMI on their model, then we could write a framework that would allow people to pick and choose models from different places, to assemble them into the framework to do more science with bigger models.
Yes, that makes a lot of sense, as opposed to like inlining a bunch of new PDEs and then doing the whole thing together.
Right, right on.
Thank you.
Yeah, thanks for your question.
So following on to that, I'm curious about kind of schemas and things like units of measure. Dominic talked about like when you define what output your model provides or what input it needs. How do you describe that ontology?
Yeah, that's a good question. So we actually have something called the CSDMS, and let me know if this answers your question, Cyrus. Sure. We have something called the CSDMS standard names, which are built on the CF conventions. And so when we ask someone to write a BMI, we ask them to basically tell us what variables they want to expose through the BMI. Those variables will have names that follow the standard names convention, so they can do semantic mediation across different models with different BMIs.
Uh-huh. Okay, so it's based on the CF conventions.
Right, yep.
And the core data structures are just like kind of different numeric formats?
Right, yep.
And vectors of those and things like that?
That's right.
Okay, great. Other questions?
Sorry, since we got a little bit more time. So how would you compare it to another approach, which would be using couplers, like Oasis or MCT or something like
Right,
that. Like,
yeah.
how does that compare in this kind of space? Because I think you could sort of see it as maybe trying to solve a similar problem, but in a really different way.
I don't know if I'm familiar with these technologies. I'm not sure if I have a good answer for you. Shoot, I'm not sure I can give a good answer. Just in the sense that, this is another way. I mean, there's other ones in the US as well. We have like Nuopsy, for example, from NOAA. These are different approaches to solving a similar problem, I guess. This is the one that was homegrown within our community. And maybe the advantage, which is also maybe a disadvantage, is that it's pretty easy to work with and pretty easy to implement.
Yeah. No, I think that's a huge advantage. I wonder, I don't know if this is right, but I'll say it and see what you think. Like, you said the Hollywood principle is, let me get it right, don't call us, we'll call you.
That's right, yeah.
Maybe couplers is like the opposite of that. Like, you have to talk to the coupler.
Right.
And so you have to know about the interface of the coupler, so it's like the inversion of that, perhaps.
Yeah, that seems to make sense. Again, I want to be a little careful because I'm not sure I can quite talk about that.
Yeah. Okay, thank you.
Oh, is that good? Okay.
I think some of those other tools that you're talking about, Dom, they inject themselves into the code. So the code becomes dependent on some of those other couplers. And we don't want that at all. We want it to be independent. So if you're using, say, our coupling framework and you decide it's crap, you can switch to something else. It's no problem. You haven't tied yourself to a particular framework.
So our issues about sort of packaging and reproducibility and dependency management, those are all part of the framework rather than the interface presented, that like this model needs a certain Fortran library in order to run.
Yeah. I'm trying to think. I would say tentatively yes. I haven't thought about that enough.
Yeah, that boundary between the two, I think, is an interesting place to
start
thinking.
Yes, yeah.
Mm-hmm. Okay. So could you give us some, so you have a bunch of users now. What is their, what have you learned from getting it out other than that, you need governance?
Yeah. Well, we learned about the need for parallelization, for sure. That's something that was a bit of a roadblock.
Can you elaborate on that? Like what aspect of the BMI?
So for example, right. So for example, like Wharf Hydro is parallelized, as is Delph 3D and ModFlow. All right, ModFlow and Wharf Hydro do similar or complementary, they tackle complementary problems in hydrology. And so having BMIs on both of these pretty big models was great, but it was currently limited because we can only do serial operations. And so it was cool that they could talk to each other through a BMI, but not cool that they couldn't be parallelized at all. So that's an example of one thing we've learned.
But let me make sure I understand here. So the models themselves, like if you think of the model as a function that takes input and produces output, in between those two, it could do whatever it wants. It can run in parallel on a GPU, whatever.
Right. Yeah.
You're saying there's something about the coupling where it's not fully run one model to completion and feed the output into another, that they're more streaming into each other?
Well, yeah, we would do times on time step. And so like basically sharing, passing values between the models at each time step.
Okay, so it's about the
two-way coupling.
It's not just function composition. It's something about a distributed system with communication. That's it. Okay. Yeah.
Right.
Interesting. Okay, great. Where are we?
Yeah, I think it's a good time to break for lunch.
Okay, yeah, we got lunch coming up here, so we'll come back after lunch and have discussions like this, and looking forward to it.
Cool, thank you.
Thank you to our speakers.